I'll add you, Tim, as a co-host as well, since you'll be presenting. So that will make things easier. Okay.
Okay, thank you.
Okay. All right. So Marwan is also here. I'm going to add Professor Marwan to be co-host as well. Awesome. All right, it's 1 p.m. and I see a lot of familiar faces. So hello, everyone. And yeah, we can wait maybe a few more minutes just since people are connecting right now. We can wait for a few more minutes. Okay, so we can perhaps wait for a couple of more minutes, then we can start since we have a short intro anyway, so then we can be on time still with the first keynote. So. All righty. So, Professor Marwan, should we start? Okay. Yeah.
Yes, sure. Please go
Awesome.
ahead.
So, yeah. Hello, everyone. Welcome. Good morning. Good evening. Good afternoon, depending on where you are. So we have people from all over the world. Welcome to this virtual edition of the International Workshop on Refactoring, held in both Sunday and Monday, depending on where you are. And on behalf of the general chairs and the organizing committee, we want to all welcome you to this event. So I want to say, first of all, welcome with all the languages, since we have people from all over the world. And this is a pleasure to have this online event, which allows us to be, all gathering under this event, virtually. So today's schedule, we will have 5 main talks, plus we will have 2 exciting keynotes, and also one more announcement that we will have, which is not appearing here, but it will happen right after the second keynote. First of all, I want to, of course, thank our 2 keynotes for accepting to give the talks on this event. We have Professor Tim from JetBrains Research, who will start within actually a few minutes, couple of minutes. And then we have also Professor Nikolaos Tsantalis from Concordia. Will also have a talk within around 2 hours, 50 minutes from now. So stick to these 2 exciting talks. We will see a lot of advanced research in both in industry and academia about how refactoring is impacting research. Also, we will have our 5 main presentations. So also stick to that. I'm very excited about them. And of course, I should first of all also thank all the program committee members who did volunteer their time and put their expertise into the service of this workshop. And without them, we wouldn't be having these sessions today. And also, I want to also extend my thanks to the organizing committees of this event. So without further ado, I think we are still exactly on time for this workshop. We can perhaps start with our with our first keynote, which is by Professor Tim. So Professor Tim, feel free to share your screen.
Yeah, sure.
Just stop.
Hi, everyone. Yeah, you should be seeing my slides now, right?
Yes.
Yep.
Okay, so thank you, Mohammed. So happy to be here. Actually, I really enjoyed this workshop. I've been attending it since 2018, I guess. It was back then, it was in Montpellier in France. And here I am today giving a keynote talk. Very excited. So thank you for inviting me. I'm going to spend some of your time today talking about how we do refactoring related research at JetBrains and the way how ideas become features in IDEs. I hope you will find something useful in our experience, and I'll try to reflect on the takeaways for the research community. So a quick intro. I come from JetBrains, a company that is responsible for bringing you IntelliJ IDEA, PyCharm, UTrack, TeamCity Space, Kotlin, and other IDEs and tools for teams. Currently, we have more than 10 million users, and the number is growing every year. We are an international company of more than 1,500 people working from 9 different offices all around the world. And aside from multiple product teams, we also have a research department containing about 20 labs now, dedicated to various topics from nuclear physics and neurobiology to, I don't know, mobile robots, cryptography, stuff like this. I personally lead a lab on the application of machine learning methods to software engineering. The lab was established 4 or 5 years ago, and the goal was to merge current state-of-the-art practices in the area of software engineering and machine learning. And we are still working on that, but I'd say that currently our research interests are a bit broader than just the application of machine learning. Software development is a complex process involving various people playing different roles and, more importantly, creating all kinds of artifacts. Some of them are known to be important, like source code. Others might be considered more of a side effect, such as code diffs in commit messages or a list of binaries used in your project. For us, all of this is input data, which we mine, analyze, and use to create new kinds of tools, helping developers be even more productive. So as we like to say, we help computers leverage data to help people program other computers. And this surely includes code refactoring, which we are going to talk about today. So my talk will not be about the best approach to recommend refactoring or something like this. We have papers for that, right? In this talk, I would like to discuss the path we should travel from an idea through a research prototype to an IDE feature. I'll try to share our experience on this journey for all of us to learn from the cases where we succeeded and from the cases where we failed. So the first thing I wanted to highlight is that the feature pipeline in JetBrains products is actually somewhat similar to the startup culture, where your main goal is to create a minimal viable product as fast as possible, get the feedback, correct your prototype, get the feedback again, and so on. So we have to make an extra step, proving to ourselves that this is a task really worth pursuing. Speaking about our research lab, we are usually at the very beginning of the pipeline. We are fishing for new ideas, we test them, and well, as the base case scenario, we bring them to different production teams if these prototypes meet our expectations. So then these prototypes are transferred to the development stage, where the prototype is usually thrown away or implemented, tested, deployed, and so on. So this is a separate large pipeline, which is a bit out of scope of today's talk. So we'll simply call it development here. But a lot of ideas and even prototypes are put on hold until we get a better understanding of what should be done, or until we invent a new technology with the desired level of quality and performance. I'll share one of such failure cases today as well. Okay, so refactoring. I'll be brief here, since I'm sure this is not the audience who I need to convince about the value of refactoring. We all know it's good for your project, for your team, for your karma, and so on. IntelliJ idea actually turned 20 years old this year. And I think we can confidently say that a great deal of its popularity, well, this idea got because of the refactoring tools it contained from the very beginning. So to be extra sure people still refactor code, we have recently conducted a survey involving more than 1,000 paid subscribers of our IDEs. And yes, refactoring is still a common practice. Well, you see, only about 2.5% of respondents did not refactor any code in the last month. And surprisingly to us, 66% of the respondents spent more than an hour in a single refactoring session. So people still need better and smarter tools for refactoring, and therefore more quality research is needed in this area. So there's some work for us to be done. The third thing that I would like to talk about today is the refactoring recommendation task. So there are dozens of papers suggesting and improving all kinds of recommendation algorithms based on heuristics, different machine learning methods, or anything else. And many of these papers report very high results. So when I was reading all these papers like 5 years ago, I kept asking myself the same question over and over again. Why don't we still have features like this in our everyday development tools? So our IDEs are known to help you perform refactoring automatically, but you actually need to sit down, make a cognitive effort, and command your IDE to do this refactoring for you. So refactor recommendation features seem like a reasonable next step to make for us. So the first story is about the project called Architecture Reloaded. Actually, this project was one of the first projects that we started when I joined JetBrains at the end of 2016. There were only 2 of us in the lab, and there were only 2 interns working with us. So it was very different from what we have now. And we were very enthusiastic about applying machine learning to software engineering. So our idea was pretty simple. Let's take the best recommendation algorithm there is, build an IntelliJ IDEA plugin around it, see if we can make it production ready. So what can go wrong, right? Well, we started to struggle with the very first step. In the papers we read, we encountered 6 different ways the proposed approaches were evaluated. So the first one was that researchers manually explored some artificial example or a small project and compiled a complete list of existing refactoring opportunities. So this could act as an example of how the algorithm works, but that's it, basically. Next, the tool is run on some considerably large project, and experts are asked to label each recommendation we get. Since the list of recommendations is usually small, this approach also doesn't require a lot of human effort, but that way it's almost impossible to say anything about the recall metric, for example. Another approach is based on software metrics. For example, we measure cohesion and coupling before and after moving the method. So it could easily be automated, but this approach highly depends on the selection of metrics, which is very subjective. And it does not allow to measure any statistical metrics as well, such as precision recall, since the data set is basically unlabeled. The idea of the next approach is to look into the project histories and collect refactorings that were actually applied by developers in the past. But it turns out that for a whole project, only a few refactoring instances of a particular type are usually found, and not in every commit, which, well, is not very effective, and it's hard to change between versions of this project and so on. Well, this approach, I guess, is the most widely used one. A group of experts is asked to go through some large, usually open source project that mark each data point. For example, say for each method, whether it should be moved away or not. It works well, except that it takes a huge amount of effort to label even one real-world project, especially if the researcher wants to have unbiased labels, meaning multiple labels for each data point from different experts. And one popular approach as well is that the approach is based on the assumption that in a real-world project, there are way more methods that are placed correctly than methods that should be moved elsewhere. Well, in case of the feature-envy code smell. So if we take a random method and move it from its class to somewhere else, feature-envy will most likely be introduced. This way, the data set could be gathered automatically, and it could be as large as we need. And I always wondered if this assumption is actually true, but okay. About a year after we faced these problems, a paper came out reporting the data that perfectly summarized the degree of frustration and desperation we had at this time. So in every cell, the tool is the same. It's J-ordered. And the task is also the same. It's recommendation of move method refactoring. But you see, the numbers are very different because of the different data sets they used. So finding the best tool basically was not possible for us. How can the industry adopt the cool results of the research community if there's no way to see which of them work better? Okay, if we cannot find the best ones, let's select the ones that had an open source implementation and we use that. But among the approaches that use machine learning, we found none with existing implementations, trained models, and stuff like this. Okay, then let us select the ones that report decent results and are kind of straightforward enough to implement. We selected 3 of such approaches. I don't really want to reference these papers here since we actually failed to reproduce any of them in our setting. We spent the whole summer of 2017 tweaking the parameters and inventing heuristics to filter false positives. In the end, we managed to build an ensemble classifier based on weighted voting to combine the strengths of these approaches. We created and published an IntelliJ IDEA plugin in the marketplace, which got around 500 downloads overall. And analyzing the feedback we got from testing the plugin ourselves and dozens of people we recruited inside the company to try it out, we realized that this prototype is not yet ready to become an IDE feature. So this was a negative result, and to be honest, quite a discouraging experience for a new emerged lab. But okay, if we take a moment to reflect and learn from this story, I'd like to point out the following. Some of you know me as an open source proponent. I have no problem with proprietary code in general. I do work for a company that literally sells software, and some of our research projects that we do are kept internally. But for all the research results we publish, there is always a GitHub repository. And I strongly believe that this is not something unusual. This should be the new normal. Sure, it doesn't solve all the problems we face, troubles with running other people's code from GitHub all the time, but re-implementing and debugging the algorithm from the paper is a waste of time. And it makes me really sad each time we have to do that. Next, not only the source code should be available, but also the data. Oh, in the perfect world, we will have a benchmarking infrastructure for every task that runs the new algorithms against the existing baselines on some labeled data set we have. We made an effort to create such an infrastructure with our architecture reloaded project, but well, we had to discontinue the project for several reasons. So maybe it's time to give it another try. It might just happen so that we have every piece of the puzzle now. I think the second keynote of today could tell us exactly how to collect. It is a data set for that. And the talk by my colleague Zarina that is happening right before the second keynote will highlight the tools we have to build such a benchmark. So if you're willing to invest in this endeavor, don't hesitate, reach out and let's do together. And the third thing that I wanted to highlight is more of a conceptual nature than technical. So the aim of refactoring is to make the code better, cleaner, and more understandable, right? But when we focus on technical details too much, we might lose the big picture. For example, a refactoring opportunity might be considered invalid because it tries to move a method that references a private field. But maybe we should not get discouraged by this. Maybe suggest a chain of refactoring operations, or just show a hint saying that this fragment of code is so awful that it could benefit from refactoring. So attract developers' attention and leave them to figure out how to make this code simpler. This is the real feedback that we got from the people using this plugin. Automation is surely important, but well, sometimes just finding a smell might be enough. And we definitely have to research more how to find balance of this in practice. Well, this is not actually something new. People have been researching this, but it's just one of the takeaways from this project we have. So moving forward, the idea to turn refactoring recommendation into an IDE feature was reincarnated within our team in 2019. Actually, it was here in this workshop in Montreal where I met Nikos Santalis, and we had several long discussions about research, refactoring, and developing tools. Good old times when we went to places and met people, right? Anyway, one of the things that we discussed is the JDeodorant tool, which I guess, again, needs no introduction here. Surely we also did know about JDeodorant before, but it was something big, dominant, and based on Eclipse. The tool is based on a set of heuristics, so we really didn't consider this approach previously because we were interested in machine learning-based approaches. Well, and to be honest, it was very scary to compete with such a force that dominated in this field for more than a decade. Talking to Nikos about how difficult it was to figure everything out within Eclipse's infrastructure back then confirmed my fears about how much effort it would take to re-implement everything for the IntelliJ platform. It's like 15 papers with their own tweaks and hacks. And migrating the existing code requires getting rid of all Eclipse dependencies first. However, the seed in my mind has already been planted. I got back from ICSI, and sometime in summer 2019, we had a chat with my colleague, Zarina Kurbatova, who is a brilliant engineer and researcher, that it would be nice to get some interns in the fall and try to figure out whether we can do something with migrating the code base to IntelliJ platform. And working with the best people has its benefits. Zarina actually dug herself into the existing code base and pulled this through. I was not surprised. I believed in her, but still. We started in September, and in October, 2 interns joined. And by New Year's, we already had feature envy and long method detection as a working prototype. From January to March 2020, we tested the code, tweaked the UI and other things. And then we published the plugin at the end of March. So here I have to absolutely give kudos to Nikos and his collaborators for taking the time and effort to develop and maintain the architecture of JDeodorant. As you can see here, it is quite modular. So the core part almost remained untouched. So we had to rewrite the code that did the parsing, user interface, and like other parts that perform refactoring operations, since we wanted to use the means provided by the IntelliJ platform, and JDeodorant used the ones of Eclipse. We also added collecting user logs. So all the fields in our logs are either enumerable or numeric. They don't contain any binary blobs, free-form text, hashes of your code, libraries you use, or anything else of the sort. We never log what you write in the editor. It would make our lives much simpler, but we don't. Well, in fact, we go the extra mile to avoid logging your code accidentally. The server parses everything we send and discards any entry that includes unrecognized information. Well, our logging policy is that everything is forbidden unless it is explicitly permitted, and many levels of reviews are required in order to change the list of what is allowed. So here's an example of an extract method refactoring being suggested and applied by the user. So for each such event, we record the following: the number of statements extracted into the new method. In the case of this selected fragment, it would be 5. The if statement, the 2 statements before it, and the statements inside the branches. The number of lines in the new method, so the selected code lines and plus the generated return statement. The number of parameters of the new method, so it would be 1, since tick date here would be a parameter. The number of lines in the original method before the refactoring, after the refactoring, and the number of parameters in the original method before the refactoring. So we collect this data just for our information and mostly for catching outliers and debugging them. However, in other projects, this kind of infrastructure is used to collect features for training machine learning models. So if you're interested, please read this series of blog posts about how machine learning is used in our IDEs to empower code completion. Okay, moving forward. So here are the links to the actual plugin and of course the GitHub repository with all the code. I don't put URLs here, so just Google this and you'll find it for sure. So we stopped actively developing the plugin in sometime in December 2020 when the last release came out. Basically, we migrated everything that was in JDeodorant, and well, that was it. But this code base surely could be extended with some other algorithms or reused for some similar project. So, well, it could be even the basement of this benchmarking platform I talked about before. So if you are interested in any of that, take this code or reach out to us and let's do something interesting together. Okay, let's continue our story. As I mentioned before, our team is a research lab. So we don't ship features, we don't create products. Our goal is to find an idea, build a prototype, and if we find it worthy, well, we get someone in the production team to fall in love with this idea and carry our flag further. And this prototype, IntelliJ Deodorant, was good. One of the PHP Storm developers, Andrei Sokolov, was very enthusiastic about the whole idea. While working on PHP Storm, the IDE for PHP, obviously, he implemented various refactoring operations. Some of them were quite complex, but our logs show that feature adoption is quite low in this field. Developers might not even know that a particular IDE feature exists, so it remains underused. So after a series of discussions he had with us and some prototyping on his own, Andrei finally decided to switch to working on refactoring recommendation full-time, which he has been doing since April of this year. But before I show the results of his work, I should tell you about the early access program we have for our products. So this program gives anyone who participates free and full access to pre-release versions of all of our software. So it allows you to evaluate new features, test issues that have been fixed, and provide feedback. And at the same time, it gives us the opportunity to test experimental things, the things that might not appear in regular releases. For example, collect logs to see how the new features are doing. And there are usually several thousand people participating in this program, so it's quite some number. There are free such EAP releases each year, which gives us free windows of opportunity to put things there, get data or feedback, and pull them back before the release if needed. So if you want your prototype to be tested in the wild like this, come to us. Well, it would surely require a ton of extra work to make it stable, maybe some UI work, but well, I'm saying that it's still doable. You can do that. In the first version, Andrei implemented the approach from the 2011 GSS paper that detected the long method code smell. So this algorithm relies on control flow and data flow graphs to find all code statements modifying some variable or some object property. So the UI was very simple. We have a list of candidates to extract. When you select a particular item, the ID highlights the appropriate code fragment, and basically that's it. So in the next EAP, they decided to try another approach and use an algorithm that searches for a sequence of statements to extract by calculating software metrics and ranking all the candidates. So this approach allows us to detect more diverse blocks to extract, not only those that calculate the value of some variable. Also, some UX rework took place. A new window for the candidates, for the candidate list has been designed and created with a preview with the signature of a newly created method. So it was a step forward. Here's a demo of how it works right now in PHP Store. So before that, there's a background process that searches for complex methods based on several software metrics. If a method is considered complex enough, this gutter icon appears. Clicking on this button actually starts the calculation, the code analysis, and it takes some time, and 3 best candidates are shown. Well, the number 3 was chosen empirically since people actually rarely examine more options, and a very long list might actually overwhelm them and prevent even from using this feature. So the extracted fragment is highlighted. Well, we can examine the preview here. When we're done, we'll select other candidates. When we're happy with our choice, we hit extract, and a standard refactoring window appears, which we can use to conclude the job, basically. So here we again preview the signature and hit refactor, and okay, we're done. So originally, finding the candidates was implemented as a separate code inspection. So, code inspections are those yellow background, yellow backgrounded code that you can click on and most oftenly apply a quick fix. The problem with this is that some users really get used to the yellow code, and eventually they begin to ignore it. And this refactoring recommendation is a new feature, so the developers wanted to attract additional attention to it. So they used this gutter icon as an alternative. Moving forward. Yep. So here's a screenshot from the latest release candidate of PHP Storm, which everyone can download and use. If you open the list of supported expansions, you can see all of the implemented recommendations there. Some of them just calculate particular software metrics and report methods or classes that violate the limit. The one that I showed on the demo is the complex function one. You can also see that there is another one concerning the feature and the smell, and the one suggesting the pull-up method. Obviously, this is an ongoing project. It's been active for like 6-7 months, and a lot needed to be done. So implement new approaches, analyze the log data, we get improve the already implemented approaches, come up with new UI, etc. And there's only one developer currently working on all of that. But the good thing is that PHP Storm is built upon the IntelliJ platform, along with IntelliJ IDEA, PyCharm, WebStorm, and many other IDEs. Yes, they do differ in some things internally, but when we get something to work for one IDE, it is much easier to migrate it to others as well. So I'm sure we'll see more of such features implemented in our IDEs for other languages, other than PHP as well. Okay, so time for some key points of this story. The first one I wanted to touch on is the angle researchers and practitioners look at the task of refactoring recommendation. Once I reviewed a refactoring recommendation paper that tried to maximize the recall of the approach. The authors backed this with an argument that, well, the more code smells we find and fix in the project, the better the code base would be. From my experience working as a software engineer for almost 10 years and observing other people writing code, this is actually rarely the case. Refactoring is usually not a separate event, such as these code reviews in the pre-GitHub era when the whole team gathered in one room, opened some file in a projector and discussed how to make it better. Well, we do tend to have long refactoring sessions to rearrange some things and make some other features possible, but I never saw people sitting down to eliminate every complex method in the project. Well, maybe this is unfortunate that people don't do this, but it is how it is. And this brings us to the question, what do developers actually want from the refactoring recommendation tool? Is it the complete list of code smells in the project? Or what are the 20 possibilities to split this particular method? From our experience, it would be something much closer to what is the one modification in my project that I can do right now and make it better without actually spending too much time on. And to do that, we need to find the smelliest place as quickly as possible and suggest the one fix and do it interactively. Well, which actually brings me to the second point. it seems like we already know pretty well what to suggest. The less obvious thing is how. The more some refactoring tool will be integrated into the workflow of developers, the greater their adoption will be. Analyzing the logs we get from the users, we see that sometimes people click on the gutter icon that I showed you, they initiate the process, but they don't get to the final point. And well, why are they lost somewhere in the middle? We don't know. I know that people work on this, and we had papers on this workshop exploring the user experience of refactoring and other practical aspects, but I think we lack enough research in this area. There was a great keynote at ICSME by Gail Murphy about a month ago on the usability and usefulness of the tools we use. And she suggested that maybe we should transfer some of our energy from developing new tools into better understanding of how the existing ones work to bring the most value from them. Well, obviously I'm paraphrasing, but this resonated with me. Well, here I am saying that we as a tool vendor are very much interested in diving deeper in this topic. If you are researching the usability and usefulness of IDE tools, including refactoring ones, come to us. I think we can help each other here. And the third thing is more of a technical one. If we're talking about bringing this tool to a real people in an immersive and non-intrusive way, the refactoring tools should be fast, like a matter of seconds fast. No one would agree to wait for 10 seconds for the method or even the file to be analyzed. The ultimate goal is to provide such an experience that a developer understands that their code becomes problematic while they're typing. And bringing all the calculations to the background doesn't really help. It overloads the CPU and drains the battery of the laptop. And well, needless to say that we're limited in memory consumption as well. So in the current implementation in PHP Storm, a lot of work has been invested in such optimizations. For example, the original IntelliJ deodorant code was not used and things were implemented simply because of these reasons. Well, our goal was to obtain a working prototype as fast as possible. So we tried to reuse as much code as we could. And this resulted in creating wrapper objects, which increased memory consumption. Well, currently, we don't have to think about all of this to write a paper, right? We compare our precisions, recalls, and other scores, but performance is as important as the quality of the recommendation algorithm. So my point here is that it would make me very happy to see papers comparing the performance of their approaches alongside with other quality metrics. And it would definitely help to adopt these features by tool builders. Okay. So here we have a story that is not going to be about refactoring recommendation, but about mining refactorings from the version control system and what we can do with this kind of data. Well, I guess this story could act as a warm-up for the second keynote of today, but anyway, I think I might get back to the recommendation part at the very end here as well. Okay, so we have a history in the version control system, and we have some tool that can detect refactoring events within code diffs. So there exist several such tools. They differ in how they do things, but I'm not going to talk about this. I will focus on the application side. So why do we need such tools? In academia, they enable all kinds of empirical research. People study all kinds of stuff mined from the VCS. There's a separate MSR conference for that. Go and check out that program. So another case that already mentioned today is building data sets, for example, to train machine learning models. But we're talking about IDEs now and how this data could be useful for a practitioner. Well, there are data-driven tools that work with code changes, for example, refactoring aware branch merging, or a tool that applies quick fixes based on historical data. All of these tools depend on mining refactoring events. But in this project, we decided to start with supporting code reviews and code exploration. In this setting, refactoring operations are often considered as noise. When you're browsing through the diff of a commit to see what changed, well, sometimes it's hard to see what actually happened because of the refactoring changes. So wouldn't it be nice to have all the changes sorted out and labeled somehow? There's a bug fix, there's a new feature, and here's the refactoring. Well, the last part is exactly what our IntelliJ IDEA plugin called Refactoring side does. So we ran Refactoring Miner on a commit to understand which changes are refactoring and which not. Then we empower this data to implement several usage scenarios, which I'm going to show you in just a moment. Here are the links to the marketplace, the GitHub repository, and the paper describing the tool, which is going to be presented at ASE like next week. But you can just Google refactoring side and you'll find all this, no problem. Okay, let's see how it works. So this is the standard IntelliJ VCS window displaying a list of commits in the project. And here we have a tab, a new tab that shows refactoring changes performed in this particular commit. So we have that, sorry, make it back. We see that there are two methods renamed and one method was extracted. So double clicking on that shows a standard diff window that shows this particular change that corresponds to this particular refactoring. So yep, that's it. One of the use cases. And it also works for pull requests if you prefer working with them within the IDE. The second, oh, this is the same. Yeah, the second scenario is more of an exploratory one. So for each method or a class in this case, you can see the refactoring history. So the history of how it's been refactored. So when you click that, a new window appears, for example, in this case, showing that a new annotation, class annotation has been added and removed after some time. So again, clicking on those shows a list of commits, the history, where you can see who did the change, what was the motivation, and when, for example. Yep. Yeah, moving forward. So the prototype was ready and it worked pretty well. So we went to the IntelliJ VCS team to get their feedback. Overall, they were quite positive about the tool, and they suggested that we support Kotlin as well. So Refactoring Miner only works for Java. It took us some time, but we managed to extend Refactoring Miner to Kotlin in a library called Kotlin RMiner. It re-implements Refactoring Miner's heuristics and refactoring detection rules. It also relies on the embedded Kotlin compiler to parse the code and extract its inner representation. Currently, it supports the detection of 19 refactoring types, which is, well, less than Refactoring Miner detects for Java, but it seems to be quite enough for a case. They have also come up with a third usage scenario, which, to be honest, is my favorite one. We can make the diff window in the IDE refactoring aware. So we can embed refactoring information into code diffs and show exactly where the refactoring code changes are. They also, I'll show you that in just a moment. They also had concerns about the performance of the end-to-end tool, having to run Refactoring Miner and stuff like this. But our evaluation on a bunch of open source projects showed that, well, the maximum median time of refactoring side on Java projects was about 50 milliseconds, and on Kotlin projects about 160 milliseconds for commit, which, well, we believe it is quite acceptable for our task. So the drum roll, the modified diff window looks like this. Here we can see that there's a label saying that this method was moved from some other class without changes. And more importantly, more importantly, there's this folder icon right here. So if we click that, we can fold. Yeah, we can fold and unfold those methods. So if you are not interested in refactoring, you can fold them and focus on the rest of the code change. So from the technical side, this project required the integration of different existing tools. So architecturally, it was pretty straightforward. We have the mining service that that does the mining of refactoring events and other and handles their storage. It uses commit miner that actually gets commit diffs using the Git for idea IntelliJ library and employs refactoring miner and Kotlin R miner tools to find refactorings in this data. We also have Diff Window, which is basically the upgraded Diff Window, enabling all the hints and folding magic. And this was one large model, which made it impossible for the VCS team to take parts of this project and move them into IntelliJ platform. So we had to split this code base into several Gradle modules. And well, we made the common component here language agnostic and independent of any specific libraries, such as the Eclipse JDK, for example. There is also the runner module that now runs all this mining and other calculations, and the plugin module, which is responsible for the UI side of things. We refactored the code that represents refactoring in Java and Kotlin, and now they can be used separately and independently of all other code, which is exactly what the VCS team is planning to do. Oh, I don't think I can tell the details just yet, but they're working on a new thing, and this refactoring detection functionality will be a part of it. So when you see a feature like this in the new IntelliJ IDEA release, you know that you've heard it here first. But again, refactoring side plugin will always be openly available for the community. Okay, let's summarize and reflect here a little bit. First of all, I'm really happy to say that there are tools created by researchers and which are used by researchers that you can just take and make a part of your product. Well, I'm talking about Refactoring Miner, of course, not about prototype, which was basically a bunch of blue code. So once again, kudos to Nico, Samea, Danny, and other people responsible for the Refactoring Miner 2.0. Then, once again, I would like to stress out the importance of working within the developer's workflow. I see a lot of research prototypes that implement their functionality as separate windows, making the complex and difficult to learn and navigate user interface of an IDE even more complex and cluttered. Our IDEs already have tons of features that almost no one knows about. So please don't add your cool feature to this list. I beg you, if you prototype adds a new window to an IDE, please think harder. Well, I'm not saying that the current workflow of developers within the IDE is the perfect one, but well, not even close, but this is what people are used to. And our experience shows that it's almost always possible to merge new features into existing tools. So that way you will drastically increase the discoverability and the adoption of your tool. And well, it is definitely hard and sometimes requires us to rethink the whole pipeline, but it pays off. And the last thing here is kind of encouragement to try new things in an unusual setting. So look at the things we know from a new angle, and it might become a foundation of new ideas, things that you didn't think about before. For example, when we learned how to detect refactorings within a commit in an IDE, a very simple idea came to us. So when a developer prepares a new commit inside an IDE, we can actually detect refactoring code changes in this newly created commit and suggest the developer to split the original commit into two, the one that creates all the refactoring and another one with all the other changes. And having our infrastructure, that should be pretty simple to do. Another idea that came to our minds while working on these two projects is that the last two projects is that the VCS information could be pretty useful in the refactoring recommendation task as well. For example, suggesting to fix a code smell in some legacy part of the system might not be the best choice. Maybe no one from the current team even knows how this code works, and there are no tests, and well, it's better not to touch this code at all. Or expanding on this thought, maybe developers would be more willing to accept a refactoring recommendation in a code base they touched and therefore know. Has anyone tried this? Well, I don't know. Even if it was not new, I think you get the point. New perspective gives you new ideas, which I guess is good. Okay, I I'm running out of time. I wanted to conclude with this diagram that I took from a PhD thesis of my colleague, Vladimir Kovalenko, and I like this diagram a lot. It shows a life cycle of a data-driven feature in a software engineering tool. So researchers in academia mostly work on data-driven techniques, publishing papers where they compare this new technique with some alternatives. Some people make an extra step and develop a prototype tool, providing other people the means to actually use this feature. It requires additional work, sometimes a lot, but to actually make an impact with your work and make this feature a part of the production level tool used by hundreds, thousands, or even millions of people, usually a lot of extra work is needed and some help from the vendor. So we at JetBrains can help you with building tools. Well, I'm not promising, again, that your techniques will become a new feature of an IDE or some other tool, but this is a very complex process. But we can help with refining the vision of what the technique should be and how to reach your users with it. We can help with building prototypes. And if you get there, we can help bring your plugins to the EAP program and test them on real developers in the wild. So please don't be afraid to make these extra steps. It is hard, but I think it's worth it. And here I would like to thank all the people who made everything that I've told you about today. First of all, my thank you goes to Nikos and his collaborators for the years of hard work and very good software they developed. Also for motivating and encouraging us to start these last two projects and the technical support and other discussions we had. Zarina Kurbatova is the main driving force of the refactoring related research in our lab. Do not miss her talk today. It could be very useful to you. And I especially want to thank her for helping me preparing this talk. I think she answered at least a couple thousand of my questions. Vladimir Kovalenko helped us to start the Refactoring Insight project and co-supervised the interns from TU Delft that worked on this prototype on this tool. Andrei Sokolov and Svetlana Zemlyanska are the people who make the refactoring recommendation features in PHP Storm. And I would also like to thank the IntelliJ VCS team for the help and feedback they provided on the Refactoring Insight plugin. And of course, our wonderful interns who were involved in all of the project that's all about today. And with that, it seems like I'm done. Thank you once again for having me here.
Yep, thank you. Thank you, Tim. It was a very insightful talk. Yeah, I'm really happy to see all this work that you and your teams are doing. And definitely it has a lot of insights for us as a community to learn. And I can see that since 2019 we've been at least progressing towards thinking about how can we seriously implement our tools and make them available for the community and also for the developers. So that's always a good direction to take. So now perhaps it's we have some time for questions. So please, if there's anyone who had questions, or we have a lot coming, sure, of course, this is good news. So Professor Santalis, you can start.
Thank you, Tim, for another interesting keynote. So I have many points here, but I don't want to take the time for other questions. So one thing that I realized after doing research so many years on refactoring recommendation is that actually the tools that we made, they cover only a small portion of the what motivates developers to apply refactoring. For example, you mentioned for move method, you mentioned feature envy, but there might be, and there are many other reasons to move a method. The same holds for, let's say, extracting a method when you have a complex method. There are many other reasons to extract a method. So what do you think about, do you think this is a reason for the adoption of the refactoring recommendation tools? Maybe we're not supporting every scenario yet.
Well, I don't think this is a disadvantage. This is a window of opportunity. So yes, surely, I totally agree with you, because Well, sometimes I extract a method only for a fragment of code that is only used once, because I want to give this fragment of code just a readable name. And calling a method with a readable name is always better than just adding a comment saying what this code does. So yes, there are different scenarios, and I think we'll get there eventually. So we have to look at them and well, one by one. Yeah, I think we'll get there. So this is a very good point. Thank you for that.
So I will address this in my keynote that follows, actually. So please, if you can stay, it would be great to.
I will for sure. Yeah, wouldn't miss it.
Thank you.
Yes, Sridhar, please.
Yeah, hi. Hi, Tim. Thanks for the excellent talk. I was just wondering, like, when the developers do refactoring for the code, what would happen to the non-code artifacts? For instance, like, the README files or the dependencies in the comments and so on. So, of course, like, the refactoring would change the code, but the implications of that, would that have an effect on any of the other non-code artifacts? In your surveys, did you find that, or do you think, what is your take on, like, how do you deal with this kind of thing? Because if the code is changed, we know that the code is refactored, but why is it changed? The rationale for it, how do we preserve that? And does it make sense to preserve that? I was able to connect with your history thing, but I was just curious to see if there are some observations or thoughts on non-code artifacts or non-code information.
This is a very good point, because for example, when you refactor code and you have some data structure connected with some ORM library or whatever, it might, so just refactoring the code, it might not be enough. For example, when you're refactoring some public API or something, so you have to, not every method should be refactored in the same way, I guess. And the thing that you said about the reasons and then connection to other artifacts, I think there's, well, I don't have the answer to be short. We didn't study this in our survey. Maybe we should run another survey on this as well. But I think this is a very interesting thing to dig, because, well, and I think that it should come from empirical study. So, well, I think we should talk to the real people and try to understand. I have my own experience, but it is limited. Yep, we have to go to developers and see what is the usage scenarios in this case.
Sure.
Yeah. Thank you for that.
Yeah. Thank you.
Yeah, thank you, Sridhar. Sridhar, everyone is asking really like questions to the point today. So we have also Faisal who wants to ask a question. So Faisal, feel free to unmute yourself and ask a question.
Okay, thank you. Hi, thank you very much. In the slide 23, you mentioned you use algorithm for searching to find a fragment of code. Which algorithm did you use, if you may, to tell me, please? And second question.
Could you repeat the question, please? The last
in
part.
Slide 23, you mentioned you are using an algorithm to find some code fragments.
Yes, it was the Haas paper, Haas and someone else.
Yeah.
Let me find it.
Yeah, it will be nice if you can paste this perhaps in the chat this way.
Oh, I see. The label was under the image, but it was black text on black background. So I will fix that. Here's the paper. Yeah, sure.
Okay, I see it.
I messed up the colors.
Yeah, so it's already on the chat. Second question, please go ahead.
And another question, please. You mentioned using refactoring recommendation tools, okay, to allocate, example, the method or classes that, let me say, highly recommended to be refactored. What do you think, like, refactoring is different than feature location concept? Like there is a concept called feature location to map source code to the software feature, for instance. Like, what do you think the refactoring tool would be really different than feature location concept, technique or tool, if you mind? Thank you.
I don't think I read enough papers on feature location to have like an opinion on this, but sometimes we find answers to our problems in different domains, and people are, well, trying to solve the tasks. And sometimes if they look at some other task that people are trying to solve, they find some inspiration there. And well, it was multiple times for me. So reading papers is good for you. I guess this is my outcome. But I'm afraid I don't have the exact answer to your question. But I think that from what I know, it might be quite similar. So maybe trying some approaches from this task to refactoring recommendation would definitely be beneficial. So
if I'm allowed to perhaps, just give my thought about this, is that
sure, go ahead.
in feature recognition, we have the whole area of traceability where we can link requirements to source code artifacts, which is a well-established area for requirement engineering. However, in refactoring, we are still not yet there to do that traceability between, how developers want to see their code and how it is actually implemented. That's maybe part of how we document refactoring, whether we do it the appropriate way or not. So that's another area that maybe we have to think about carefully before, so that we can support such feature revocation, for example. That's perhaps my thought. So, thank you, Faisal. Very, very exciting questions, Professor Marwan.
Yeah, sure. Thanks, Tim, for the really very interesting talk and really an excellent, takeaways that you shared. Great job. So basically, I have two questions for you. So, my first question, we actually performed recently a survey. It was mainly with, with government organizations, that include U.S. Department of Defense, about their needs. And we were actually very surprised with this organization. They have actually a huge need for large-scale refactoring. So I know what you presented today is more for incremental refactoring, but actually they have really huge need for large-scale refactoring, and they really struggle to find tools. I mean, for those type of large-scale refactoring that could be including, for example, microservice migration, this kind of thing that requires some very extensive refactoring first. So of course there is a belief in academia that large-scale refactoring is rare, but actually found through that survey is actually very important in so many contexts, and industries almost crying for this kind of tools that are really missing to enable that large-scale refactoring. So my question is more around what we heard from them about why they think existing tools may not be adequate for this large-scale refactoring. They're always telling us that most of this large-scale refactoring are feature related and mainly business, I would say. It's not really feature, it's business related, and this business needs and requirements in general, they're documented in natural language, and then it's hard, to link, this business need to existing tools of refactoring, kind of mapping, probably some quality metrics to this business need, and it's really hard to adjust that. So that's one of the main feedback that we actually got, and then the second question that I have, it's more around this idea of mining refactoring, trying to use the history of the refactoring. So basically this is great, and one of the challenges that we faced was more to understand the rationale of this refactoring, because we look at, for example, commit messages, pull request description. In general, either you don't find anything there, useful, or so it's really hard to understand automatically any rationale of refactoring by just looking to documentation or even looking to the quality metrics before and after, because most of the time this is not the real intention of programmers that And again, it's related to the first question because many of those refactorings are related to the business needs. But currently, we all know that in existing research, this is probably, an understudied area. So anyway, I don't know if there are a question, but there are more general insights. So anyway.
Yeah, that a thought appeared. So I think that originally refactoring was more of a technical thing. So we need to move a method or we have to extract a method. But now we're talking about like the broader picture about the refactoring that happens in the minds of developers that affects this architectural things in the project or in the system. And this is way more complex and well, so there are things to study here as well. And I think this is more high level refactoring. Maybe it's not even refactoring in the original sense because it might even change some functionality, but it's still like some massive change of code that we need to be reliable. And yes, we need tools for that for sure, and we need to study this. Yeah, thank you.
Thank you.
Any other questions? I mean, we're almost up, but we can sneak one more question if anyone has any more questions.
Oh, if you have any questions, just feel free to drop me an email or tweet or whatever.
Chat.
I will
still have the chat here.
Or chat. Yeah, I'll be here for the whole workshop.
Awesome.
I'll send the slides to Mohammed, I guess, or maybe tweet them so they will be available.
Awesome. We'll add them to the website. Yeah.
Okay, that's great.
Sure. Awesome.
So thank you once again for having me.
Oh, thank you. Thank you. And thank you all guys for coming, and thank you for this awesome talk, Professor Timofey. So I think one thing we can do now is to sneak in the announcement by Professor Marwan, who wants to talk about actually one of the important things that, or one of these things that stuck to my mind in Professor Timofey's talk was, the need for community effort to build benchmarks for refactoring, So maybe this is a good opportunity for us to do this announcement for a few minutes, then we can start our first session. So Professor Marwan, please feel free to start.
Okay, thanks, William. So I think this is directly related to the keynote of Tim, basically, because he highlighted a lot in his takeaways about the lack of a community infrastructure for refactoring, whether from data perspective, but also from orchestration as well of multiple refactoring tools, because one of the struggle that we may see now probably in our community is like the lack of also orchestration between different refactoring tools, some of them about documentation, some of them about detection, some others about detecting changes or recommendation, but we may need a platform that can actually be kind of a plug and play platform where you can orchestrate all of these tools together and synchronize between them to kind of cover a whole cycle of refactoring. And this is actually something that we're discussing during the previous edition of this workshop. And we are trying actually to submit an NSF proposal around this community need, and that's involve different US researcher here because submitted to NSF, but doesn't mean that you cannot contribute. And that's what we are seeking through this probably proposal, to hear your feedback about this, any challenges related to the needs of this infrastructure. And also, if you are supporting, this idea, we look forward to also get your involvement. Like, we can get in touch to try to get some letters of collaboration, and hopefully this will get funded. So basically, here is kind of a summary of the needs and the benefits, and who are the potential users of this infrastructure. So in terms of user, we are thinking about refactoring researchers like you, or new community members, like people probably, it could be new PhD students, like they never worked on refactoring research, so they need a starting point, but reproducing existing research or having an infrastructure that make it easy for them to get into the field quickly could be a need for them. Or it could be researchers from other fields that want to use refactoring. And also the same thing for the STEM researcher and practitioners, where they want to have kind of early access to these tools, see how they can adapt them. Or also for educators, those who are teaching software quality insurance courses or even refactoring courses, they may need examples to actually illustrate this complex concepts in the classroom. So, so mainly, I mean, this infrastructure will bring different needs. So first of all, we want to provide the benchmarking platform where we actually can have thousands of projects with their history of refactoring, quality metrics, and their documentation. And also we want to basically provide a pipeline on how we can sanitize this data, how we can remove probably irrelevant refactoring, irrelevant, I mean, changes, and also trying to also build an orchestrator based on, for instance, the Kubernetes, because our idea is to kind of migrate or kind of generate a version from existing tools by the community as a service. So our idea is to build a pipeline to try to Dockerize many of existing refactoring tools and then just orchestrate, I mean, their execution on a specific project. We are talking, for example, about large scale refactoring. So you may need to actually go beyond just recommendation. You may need to run first detection, then prioritization, then so basically the idea is to enable through, for example, the containerization of many of existing tools and try to use, for example, the Kubernetes to orchestrate the use of this tool. And of course, that may require some also alignments between the inputs and the outputs of existing research tool and refactoring, which is, by the way, something, as we all know, missing now and should be probably addressed. And also looking to other trending areas in refactoring, like refactoring for data science code, including Python and so on. There are recent advances in that research as well that we want to integrate. And basically the benefits of that, it will improve, I mean, reproducing existing research. It also enhance, I mean, new research direction, being able to facilitate the integration of this refactoring as a service. So our idea here is to even enable this refactoring on the cloud, I mean, and using them as a service. So this is kind of an overview of the architecture, how we see, I mean, the different features that we'll be implementing, and we are, as I said, our idea is to Docker all of these existing tools on refactoring and then enabling their easy orchestration as well. And it will be through even an easy API that could be used even by people who are not expert in programming in general. Like in another project, for example, we found that even people who are doing research in physics and chemistry and so on, they are looking how to refactor their scientific code, and they found that using many of existing tools is actually complex for them. So that's why we want to use it for them as kind of a black box that can include even explainability of those refactorations. So this is kind of really an ambitious project that we'll try to run it hopefully for around 3 years, where we'll be collecting data from the community, collecting existing tools, trying to Dockerize, I mean, many of this existing tool, providing that support to actually enable this refactoring as a service and providing the documentation and doing all the community building through, I mean, this other venues to continuously hear the feedback, and that will be done during the whole project. And basically, I mean, if you are interested and enthusiastic about this project, we'll be happy to reach out, hear your feedback, and how you can participate with us in future brainstorming and probably providing either your tools or probably your feedback about the platform that we'll be releasing as open source. So if you are interested, please feel free to to reach out to us. And if you have any feedback now to share it with us about your needs and what you want to see, please feel free to do so right now, and we welcome any questions. So thank you so much.
Thank you, Professor Marwan. Any flashing questions for him? If not, then we should be perhaps starting our first session. So yeah, feel free to reach out to Professor Marwan as well through chat in case you have any specific questions. And now should start our first session. I'm going to put the speaker into a co-host. So that's already done. So feel free, Rui, to share your screen. So our first session will start with the first paper to present, which is called Automatic Repair of Java Code with Timing Side Channel Vulnerabilities. So Rui, the floor is yours. Please go ahead.
Thank you. I hope everyone can hear me well. My name is Rui Lima. I'm a software developer currently working at Sky Technology Center in Portugal. I'm here to present my work on automatic repair of timing side channel vulnerabilities in Java code. This work was developed as part of my thesis in my master's degree at Instituto Superior Técnico. The workshop paper was a joint work with Professor João Ferreira, my supervisor, and Professor Alexander Mendes, my collaborator. During this presentation, I will do a quick introduction to the topic, present some background and related work necessary to understand the problems and the solutions. The solution that I propose, how we evaluate the work done, the conclusions that we took from the work, the limitations that we identified in our solution, and the future work that we can do to improve the program. As everyone here knows, software is increasingly more present in the world. Today, companies from different areas use software, and given the presence of software, it must be as secure as possible, since any failure can result in the loss of millions of euros in revenue or losses. Those failures can even cause health and well-being problems to millions of people in the world. There are many kinds of bugs and vulnerabilities. Bugs can be detected using software tests, where the quality and coverage of the test determines the chances of finding a bug. But the same is not true for vulnerabilities, since a vulnerable application can pass all tests and even fulfill its specification. The kind of vulnerability has an impact on a difficulty level in detecting said vulnerability, and one of the hardest vulnerabilities to find is side channel vulnerability. Side channel is any observable side effect of a computation. These side effects can manifest themselves in a variety of ways, be it computational time, power consumption, sound production, electromagnetic radiation, etc. In some cases, these side effects can be exploited by attackers to take advantage of systems. There are multiple examples of real-world applications and systems that have been reported to have timing side channel vulnerabilities, such as Xbox 360, the library KickSat from Google, the Apache FTP server, and the Outme Reloaded. Our goal in this project was to investigate how to use refactoring to fix timing side channel vulnerabilities in an automatic way. And the timing side channel vulnerability happens when a secret can be discovered based on the computational time of an application. And timing side channel vulnerabilities can happen in several ways, which can be grouped into three different groups. Them being early exit, control flow based, and mixed timing side channel vulnerabilities. Now to start with early exit timing side channel vulnerabilities. This happens when a method contains more than one exit point that affect the method execution time. As we can see here in this example, this method contains three returns, meaning three exit points, and one of them exists inside a for loop, which means that will have a great effect on the time of the application takes to complete. For instance, if an attacker tries to understand the password that he doesn't have, he can understand the size of the password from the first return, because you will see the time it takes to complete, and from the second return, he can understand character by character the password that he wants to discover. To correct this kind of vulnerability, it's necessary to ensure that the method only has one exit point, meaning only one return, And this can be done in a very simple way by returning a variable, and instead of returning inside the for loop, simply store the value that would be returned in a variable, and that is returned in the end. The other type of vulnerabilities is control flow based. This happens when a significantly slow operation is executed only when a condition that depends on a secret is met. As an example, here is a code that contains this type of vulnerability. As you can see, if the condition inside the if or inside the for is met, two slow methods will be executed, them being multiply and mode. This can help the attacker understand the secret that he is trying to discover. And to correct this kind of vulnerabilities, it's necessary to ensure that the execution time of the method is similar regardless of which branch is executed. Meaning the time the functions takes to complete should be independent on the secret. The problem with this type of corrections is that we are adding computation operations that have no computational value to the method being executed. As an example, here is a correction of that vulnerability. As you can see, all you have to do is add an else statement and the same calls to the same methods, but those are not stored in the variable since their value doesn't matter. It will only slow the execution of the method. The other type of vulnerability, the mix, happens when a method contains both the early exit and the control flow based time extraction vulnerability. As you can see here, an example, it contains an early exit, several exit points, 3 in this case, and a control flow base, since the condition of the second if on the else, we have a slow operation being the cycle. To correct this kind of vulnerability, it's necessary to correct both types of vulnerabilities, the early exit and the control flow base. This can be done in different ways. One is to correct the two types of vulnerabilities at the same time while analyzing the code. And the other is to first start by correcting one of the types, for example, early exit, and then do another pass by the method to correct the second type of vulnerability, in this case, control flow. As an example, it is a correct version of that method where we have no longer the control flow or the early exit vulnerability. Now, a little bit of related work necessary for this project. In 2017, Timus Antonopoulos et al. Developed Blazor. That is a tool aimed at detecting time extraction vulnerabilities. Instead of using self-composition, where it has to reason about multiple executions at the same time, the authors use decomposition, where it's proved a non-relational properties about an execution. The Blazor is sound. As such, if there is a vulnerability, then it will report it. To test the tool, the authors executed against a collection of 25 benchmarks, 12 and built by the authors, 7 from the literature, and 6 fragments of DARPA's Stack Challenge. In that same year, GHM et al. Presented a new tool called Themis. This tool uses the notion of epsilon-bounded non-interference that indicates that regardless of the secret, the execution time of the application cannot vary more than epsilon. To verify the epsilon-bound non-interference, the authors present a new logic called quantitative Cartesian OR logic. The dynamic features of Java pose a challenge for Themis. For example, the reflective calls, dynamic class loading, and exception handling. To validate the application works as expected, the authors run Themis in several Java real applications, in the same examples used for Blazor, on a benchmark of DARPA Stack project, and in 7 other benchmarks with known vulnerabilities of Ether. In 2019, Shirin Muizadeh et al. Presented Diff Fuzz that uses fuzzy to detect time extraction vulnerabilities. This tool uses American Fuzzy Law to mutate the inputs in order to maximize the code coverage and the resource consumption. Since AFL only supports programs written in C, C++, and Objective-C, and that the difffuzz is written for Java, the authors use Cleansi that provides instrumentation for Java programs. The users must create a driver that, using the inputs provided by the AFL, will execute 2 copies of the code, measuring the cost difference between the two. This cost difference will be used to guide the AFL in the generation of more input values in a way that the difference can increase. This process is repeated for a predetermined time or until the user cancels the tool execution. In the end, a Python script analyzes the file produced by the multiple executions, creating a final file that indicates whether or not there are vulnerabilities present. Unlike the previous tools, difffuzz uses a dynamic analysis, and despite being focused for Java, can be used for programs written in any language. This tool was tested in the same application used for Blazor and Themis, as well as several other Java applications, such as Apache FTP Server and Outme Reloaded, as well as examples of DARPA's Stack program. Difffuzz was able to find the same vulnerabilities as the other tools, and even found vulnerabilities on the corrected versions of Blazor and Themis benchmarks. Since difffuzz conducts a dynamic analysis, and given that fuzzing is random, the authors executed difffuzz in each application 5 times for 30 minutes each time, and reported the average result. In this project, we created the tool called Diffuzzar, a tool that attempts to automatically remove timing side channel vulnerabilities. This tool works in conjunction with difffuzz and is divided in 2 parts: driver processor, where the driver is analyzed in search for the vulnerable methods, and the correction of vulnerabilities. Here we can see a high-level view of how the tool works. And to create the models driver process, early exit correction, and control flow correction, it was used the tool called Spoon, that is a library that allows to analyze, rewrite, transform, and transpile Java source code. With this library, it was possible to have an AST, abstract syntax tree, of the code, which helped in the analysis and subsequent modification. In the driver process, difffuzz will use the same driver used for difffuzz. Following the necessary pattern for the drivers created for difffuzz, before invoking the vulnerable method, it is necessary to invoke the method mem.clear. This way, the tool will search for that method and it analyzes the next instruction. The search for the vulnerable method is done twice, because the vulnerable method is invoked twice in the drivers, and this way it is possible to identify which of the parameters are secrets, given that they will be those where a different argument is used on both invocations of the method. This tool also obtains the path for the class file. Now to the part of correcting vulnerabilities. This part is divided in 2 sections. First, it is corrected the early exit time instruction vulnerabilities if the method contains more than one return statement. And then it is corrected the control flow based time instruction vulnerabilities. To correct the early exit time instruction vulnerabilities, it is necessary to remove every return statement except the last. However, the method must keep the same output for the same input. For that, the tool does not just eliminate the return statements, but modifies them in a way to keep the return value in a variable. If the last return of the method does not return a variable, a new variable will be created to hold the value to be returned by the method. And that variable will be initialized with the value returned in the last return statement and with the return type of the method. There are situations where the early exit exists to protect future operations done on variables. For instance, ensure that the arrays have a certain size or that the inputs are not null. And it is necessary that Diffuzzar keeps this protection. So every time a return is inside a then block of an if statement, the condition of of that if is stored in a map, and then it will be used to protect future access to that variable. Then it is corrected the control flow based timing such vulnerabilities. To correct this type of the vulnerabilities, the tool starts by creating two lists. One to store the public parameters, which is a final list, and one for the secret variables. This list will be updated throughout the method analysis by adding variables where its value depends on the secret. After that, the tool analyzes various instructions of the method to try and make its execution time as independent of the secrets as possible. For that, the tool tries to make the number of iterations in any cycle dependent on public parameters and not on secrets, and makes the 10 blocks and else blocks of if statements as similar as possible. This tool was evaluated in two phases. First, it was validated that it was semantically correct, and then it was verified that the vulnerabilities were in fact correct. First, with the semantic correction, we used EvoStreet to generate tests for the examples used, since there were a lot of examples and none of them contain tests, and will take a lot of time and possibly a lot of errors to have the tests ready. The tests were generated, then the vulnerable method was replaced by the method created by Diffusar, and the tests were executed again to validate that the correction was valid. Then we need to validate that the vulnerability was in fact corrected. And to do that, we use Difffuzz to search for vulnerabilities. Difffuzz was executed on every example for the safe version of the example when it was available, on the unsafe version, and on the corrected version done by Diffusar. The obtained values were then compared to decide if Diffusar corrected or not the vulnerability. The tool was tested using the same dataset used for Difffuzz. This dataset contained 32 examples. However, not all of those examples were possible to use, since the vulnerability was not possible to identify, or it wasn't early exit timing side channel vulnerability, but on other types of side channel, for example, size side channel. The solution created semantically correct versions for the 22 examples. Here is a table showing the results that we got from the execution of Diffusar. The tool was capable of correcting 14 of the examples. If we consider every example, meaning 32, then we can consider the tool as a success rate of 43.7%. If, on the other hand, we only consider the valid examples, meaning 25, then the success rate increases to 56%. If only the examples where the correction is semantically correct, those are 22, then the success rate goes to 63.6%. To conclude, the goal of this project was to develop a tool capable of automatically correct timing side channel vulnerabilities in Java code, and for that it was created Diffusar. During the development of this project, patterns and computations that lead to timing side channel vulnerabilities were identified. And besides that, algorithms capable of correcting timing side channel vulnerabilities were proposed and implemented. The tool created was evaluated using Difffuzz dataset. And despite the results showing that the tool can improve, Diffusar can be used as a starting point for the development of new and improved tools capable of correcting timing side channel vulnerabilities. Now, some limitations of the system. The system might not repair the vulnerability and can also break some of the functionality of the method. That's why we validated that the result was semantically correct, and as you can see, not all of them were, despite the majority being correct. The tool also assumes that the vulnerable method is invoked inside the driver. And if for some reason that is not correct, then the tool will fail to correct the method. And the ability to correct the vulnerability is dependent on the instructions of the method that caused the vulnerability, being that we must program how to correct certain vulnerabilities. And the other failure is that if the tool is executed on the corrected version of the control flow based time channel vulnerability, it might break that correction because we'll try to correct the same thing again. As future work, we propose to add the ability to repair more types of time channel vulnerabilities and even other types of vulnerabilities. Improve the integration of the tool with Diff to make it user friendly, and even transform the tool into a plugin so that it can be used in every build process. Thank you. This was my presentation. You can see here a link to the GitHub repository where you can find the codes and several reports showcasing in more detail the tool and everything that's done to achieve the process. Thank you.
Yeah, thank you, Rui. It was a very good, interesting talk. And yeah, I was like collecting a lot of questions for your presentation and you kept answering them one by one as you were presenting. So before I ask one question, so maybe we see if there are any questions from the audience. Yes, Faisal, please.
Yeah, hi, thank you. Let me say, if you back to the slide number 15, is your solution based on dynamic analysis or static analysis? Because I see you mentioned execution time, I think. So is your solution static analysis or dynamic analysis?
My solution does not do a valid analysis. Sorry, it does a static analysis in the sense that it will analyze the source code. It won't run the code. However, we have to first use Diff first. That is a tool that is also open source and presented in a paper. And that tool uses dynamic analysis. So in a sense, we have to do both types of analysis.
Sorry for taking your time. When you said you do dynamic analysis, like, I mean, do you use execution trace, I mean, to analyze it, or you didn't analyze the execution trace, just analyze the source code itself?
So only the source code. We check if teaching, yes. We search for the source code. Oh, sorry, go ahead.
Okay. And the last questions, in this diagram, you said search for invocation of vulnerable methods, and then you retrieved the vulnerable class. So I do believe you use information retrieval techniques here. Which information retrieval techniques do you use here, if what I said is right?
I'm not sure of the technique. Basically, we analyze the driver and we search for the instruction mem.clear, and we assume, given all the examples in Diff that the vulnerable method is invoked right after mem.clear, and we take that invocation to find the vulnerable method. That's one of the downsides of our approach, is that if the driver is not properly created, we will not find the vulnerable method.
Okay, so you are using technically the abstract sentence tree to find those invocations, right?
Yes.
Oh, that's perhaps what Faisal was trying to answer. Like, how do you find those invocations? So this is through the abstract sentence tree. Okay.
Yes, we use that for the analysis and the correction.
And this is part of static analysis. That's how it's statically coming up with this information. Yep.
Yes.
Yeah, thank you, Faisal. Very good question. So, and I really like also, Rui, how you came up with your own limitations for this work. So that's definitely something we should all do, like broad, advantages and limitations. And one question that I had was about the behavior preservation, but you did answer that already. That sometimes you break, the behavior of the method, but again, that's also one of the limitations. So my question is, what is the main reason for that? Like, what prevents you from preserving the behavior?
It depends on how the vulnerable method is constructed. The way we correct the method is we found some ways that vulnerable methods are constructed, like the multiple returns, the different number of instructions inside each branches or cycles. And we try to make it as symmetric as possible. However, when we do that, sometimes we are not able to keep the protection of certain instructions, like checking an array. We don't keep that checked sometimes. It depends on how the code is constructed. For instance, if we use a variable to verify that an array is the right size and another to access the array, we will not be able to keep that protection. That's one of the limitations on our approach.
Makes sense, yeah. And maybe perhaps you already mentioned that the usability and UI should be improved or as part of your future work. So, yeah, it may good. Obviously, having a vulnerability is very bad news. So perhaps if you are doing these changes or recommending these changes, and then maybe you can always tell developers that maybe this change will not preserve the behavior, and then let them decide about how to handle that, right? So
yeah, one of the things we do is that we don't replace the vulnerable method. We create a copy of that method that has a different name, similar name, just a modification added at the end. That way the user can validate the difference and help them identify the vulnerability and the correction.
Make a decision, correct, yeah.
Yep.
Thank you for your presentation. Thank you for this good talk, and it's very informative. And yeah, I mean, we're a bit late, but I think not much, so we can perhaps start.
Sorry about that.
Yeah, no, it's okay. It's not your fault, actually. No, no. Actually, there's a lot of good stuff and good questions. So we're a bit late, so that we will start immediately our next talk. So let me go ahead and add John as a co-host. John, you're all set now. Okay. So our second talk is by John Cook, Kim. Good to see you again, John. We met back in Montreal. Good to see you again. And John's presentation today will be about statistical analysis of refactoring bug reports in Eclipse Bugzilla. Please go ahead.
Thank you. So yeah, I'm going to talk about statistical analysis of refactoring bug reports in Eclipse Bugzilla. I'm Jong-Woo Kim, the second author of the paper, and this is a joint work with my graduate students at Westchester University. I teach refactorings and design patterns in my software engineering course. In the course, students learn that from the perspective of program evolution, a program is developed through a sequence of code transformations. For example, from the initial program P0, we apply code transformation T1, T2, T3, and Tn to map P0 to Pn. And also students learn that when the code transformations are behavior preserving refactorings, we can retrofit a design pattern into an existing program without changing the original program behavior. This idea has been introduced over 15 years ago. The Karyavsky's textbook, Refactoring to Patterns, explains how we can retrofit a design pattern by applying a sequence of refactorings step by step. But the problem is that we cannot use current IDE refactorings as building blocks. The reason is that the current IDE refactorings are flawed by so many bugs. Eclipse JDT is one of the most advanced Java IDEs, but JDT refactorings incorrectly change the original program behavior and/or produce illegal code that even cannot compile. Other major Java IDEs, including NetBeans, Oracle JDeveloper, and IntelliJ IDEA, are not different at all. That is the reason why scripting a sequence of refactorings to automate design patterns is simply impossible, although the idea has been introduced over 15 years ago. No one will repeatedly invoke erroneous IDE refactorings. Okay. So we wondered the current status of JDT refactorings, and we looked into Eclipse refactoring bug reports in Eclipse Bugzilla system. We first collected 4 bug reports containing keyword refactor the title or description, and then we manually inspected each bug to filter out unrelated bugs. And we finally found 5,000 JDT refactoring bug reports out of 22,000. I will first introduce a few, or just 2 bug reports. This is Eclipse Bugzilla bug number 420726. So here are 2 classes in Java, class A and B, and class A has member method M, and M has a parameter X of type B. And the parameter X is used on the left-hand side of an assignment. When we move the method M from class A to class B using JDT move refactoring, the X on the left-hand side of an assignment becomes this keyword. This is simply a syntax error in Java. And this bug was reported in 2013, and that is still reproducible in the latest Eclipse JDT. And the current status of this bug is closed want to fix, which means this bug will be permanent if no one reports again or requests to open again. Another example, Eclipse bug number 455540. Here are 3 classes in the same package P, class A, B, C, and class A is a subclass of C. And class A has member method M. It has a local variable X, whose type is class B in package P. Now I will pull up the method M from class A to class C using Eclipse JDT's pull up refactoring. After refactoring, the local variable X type B changed. It's now references the class B in package Q, not package P. So the type binding changed. I reported this bug in 2014, and this bug is still alive in the latest Eclipse JDT. And the current status of the bug is assigned. That means no one knows when this bug will be fixed. Okay, all right. So now the first author of this paper, Eric Lager, will present our work, the main topic of our work, but Eric is not available today. Instead, he recorded his voice.
So we wanted to do statistical analysis on JDT refactoring bug reports and answer for ourselves the following research questions. First, How many JDT refactoring bugs will not be fixed? How many duplicate bug reports exist in the Bugzilla system? How long has a bug remained in the Bugzilla system? What is the average amount of time passed before a bug is looked at by Eclipse committers? How long does it take for a refactoring bug to be fixed? And more. We first broke all of the refactoring bugs up into their resolutions following Bugzilla's categorizations. First, a duplicate report means that the same bug report already exists in the Bugzilla system. Second, bugs are marked as fixed after a solution has been implemented. Invalid means the issue is not a bug. Won't fix bugs are bugs that will not be fixed. And works for me bugs are bugs that are unable to be replicated. We counted each of the bug resolutions. Duplicate bugs make up 14.7%, fixed bugs 48%, invalid bugs 2.8%, won't fix bugs 18.4%, works for me bugs 8.4%, and the remaining unresolved bugs make up 7.7%. As you can see, there are two outliers. Duplicate bugs, which make up almost 15% of all refactoring bugs, and won't fix bugs, which make up about 18% of refactoring bugs. More on those two later. A data point we wanted to first describe is the trend of reported bugs per year compared to the trend of closed bugs per year. On the x-axis, we have the years, and on the y-axis, we have the amount of bugs reported or closed per year. Looking at the blue line, which is the number of bug submissions, we can see that there is a steady decline in bugs reported after the third year, 2003, since the Eclipse IDE was open sourced in 2001. But the resolutions have two distinct spikes in 2009 and 2019 to 2020. These spikes can be accounted for by won't fix bugs. I will explain this reasoning in more detail later. First, we need to talk more about won't fix bugs. Again, the won't fix bugs are bugs that the Bugzilla team has decided to not fix. 929 of the bugs we scraped, or 18.4%, will not be fixed by the Bugzilla team and have been closed. The majority of the won't fix bugs are closed by an automated process called Eclipse Genie. Eclipse Genie is a bot that performs automated tasks, such as closing bugs with the message below. It says that this ticket hasn't had any activity in a while, or just has not been looked at yet. Bug number 458464 is a great example of a won't fix bug. To explain what is happening, we have three classes, A, B, and C. Class A is the child of Class B, and Class B is the child of Class C. Class A has a field variable f and a method m. Method m is printing out the value of ancestor Class C's field variable f. Since Class B does not have a field variable f, it is printing out 1, the value of Class C's field variable f. When we perform a pull-up refactor on both method m and Class A's field variable f, the behavior of the code changes. Eclipse Refactoring incorrectly updates the reference to f. After refactoring, method m has a reference to Class C's f, whose value is 1. The reference binding changed, and the output has also changed from 0 to 1. JDT's pull-up refactoring has a flaw in its code transformation rules. This bug was reported in 2015, 6 years ago. This bug is still reproducible in the latest version of Eclipse as of 2021-09, and this bug was closed as won't fix in 2020 with 0 updates to the ticket. Bug number 26374 is another great example of a won't fix bug. First, this bug was reported in 2002, assigned as resolved in a month, and again in 2003, changed to won't fix in 2009, was reassigned with major severity in 2010, where it then sat unchanged for almost a decade before being closed by the automated Genie process. Here are 2 figures. The left one is resolution time versus modification time for all refactoring bugs. And the right one is resolution time versus modification time for only won't fix bugs. The x-axis is the amount of time it took for a bug to be closed, and the y-axis is the amount of time it took for a bug to be first looked at. Bugs that appear on the 45-degree line were closed at the same time they were first looked at. Bugs below the 45-degree line were closed at a later point after the bug was first looked at. Bugs aligned with the x-axis were first looked at on the same day when they were reported, but took much longer to be closed. Looking at the leftmost graph, we see that the shape of the graph is not what we would expect. Instead of most of the bugs occurring around the origin, there are many outliers further out on the x-axis and the 45-degree line. Bugs that lie out on the x-axis are bugs that were first looked at close in time to when they were submitted, but took a long time to close. Bugs that lie out on the 45-degree line are bugs that took a long time to be first looked at and were closed as the first action on that bug. The graph on the right is the same graph, except solely consisting of won't fix bugs. As we can see, won't fix bugs account for many of the outliers on the left graph. This graph on the left is the same as the one on the left of the previous slide, but this time it is being compared to the same graph excluding won't fix bugs. This graph looks much closer to what we would expect from this scenario, with most bugs existing close to the origin, signaling that they were looked at and closed relatively close in time to when they were submitted. This confirms that many of the outliers we see on the left graph are won't fix bugs. Here is the same line chart we saw earlier, but this time we included the won't fix bugs resolution trend line overlaid in the green color. This shows that the spikes in the resolution trend line are almost entirely accounted for by won't fix bugs, and proves that on 2 separate instances, Eclipse closed hundreds of valid bugs that had not been resolved as won't fix, leaving these issues to continue to affect Eclipse users to this day. Finally, we found and plotted a histogram for the average amount of days before a bug is first modified, and the average amount of days before a bug is assigned a resolution. The average amount of time it took for a bug to be first looked at was 26 days. On average, it took 674 days to close a bug. The means are 1 day and 42 days, respectively. The disparity between these two statistics is due to the duplicate and won't fix outliers mentioned on the previous slide. The mean values are small, but the more important information to take away from these graphs is that there are bugs that exist that took thousands of days to be first looked at and took thousands of days to close.
So conclusion, we found 5,000 Eclipse JDT refactoring related bugs reports, and we found 7.7% out of the total unresolved bugs and 18%, 4% want to fix bugs, which means there will be hundreds of want to fix bugs which will not be fixed if we don't request to reopen or fix. But still, I would agree with Dr. Brandt and Dr. Stamen that if the correctness of refactorings is less considered, the refactoring tools can be still useful. But I personally think that we cannot build anything on top of quicksand. We need solid refactoring building blocks. Thank you.
Thank you, Professor, for this insightful presentation, and definitely have a lot of questions to this, but maybe start with the audience. Yes, Professor Nicholas?
So I have been working for many years with Eclipse for J deodorant, and later on Refactoring Miner also uses the Eclipse JDT parser. So I was also reporting several bugs, and I had recently the same experience that this genie came and closed a bug report for which I even had the paths there. So it's really, I don't know how can I say, but I mean, there are many research teams that invested their entire infrastructure on Eclipse JDT, and it's really sad to see that all this effort to report bugs, like real bugs, these are not, they're completely ignored. So maybe it's not a good time to invest building your tools around Eclipse JDT anymore. So there are other directions to move, and probably the most prominent one is with JetBrains. So that's my comment, just to add some more to the conclusions of the paper. Thank you.
So as I mentioned earlier, the problem is that other major Java IDEs are not different. In my 2019 IWoR workshop paper, I compared move refactorings between Eclipse and NetBeans, IntelliJ IDEA, and Oracle JDeveloper, and I showed that Eclipse JDT is the most reliable tool among them. But still, I showed that there are code transformation flaws in move refactorings in all Java IDEs. And today, I also showed that there are a bunch of refactoring bugs. Yeah, I just wanted to show you the current status.
So one of the points in Gail Murphy's keynote that gave to ICSME like some months ago was that one big problem is that the refactorings the IDEs perform are not what the developers expect. So in some cases, they get results that they were not expecting. And I think these are cases like that. So there, what do you think is the problem? Is the problem on the mechanics of the refactorings? They're not so formally defined? Are we missing scenarios? What do you think is the problem?
Well, I feel like we will need to do some research or investigate the Eclipse refactoring implementation in detail. But the simple reason is that Eclipse people are not working hard. During my PhD, I reported a bunch of JDT refactoring bugs. And early 2010, I received frequently bug fixes. But after mid 2010, since then, I received more Eclipse Genie bot messages rather than repair messages. So probably we need to work harder.
Thank you.
Yes, Tim.
Yeah. Oh, thank you, Jean-Luc, for the talk. I maybe not have the question, but maybe what do you think could help to change the situation? So maybe some insight of what tool builders should do to prevent this situation, because this is bad. and I remember your talk about IntelliJ idea back then. It was interesting to to see it from this angle. So apart from test more, what could you recommend to tool builders to maybe prevent this from happening?
Well, I don't know, but my PhD dissertation topic was to automate design patterns. So I needed the primitive refactorings to use as building blocks. But I quickly realized that it's not possible because of the obvious reason. That is why I implemented my own refactoring tool, taking a completely different approach in 2016. My work was published at ICSI 2016. But my tool had still some limitations. One of that is I cannot implement every single refactorings. I just implemented some of the refactorings that are needed to automate design patterns. So, I think it's time to rethink about the way to implement a refactoring tool. But if the Eclipse people or you can easily fix the current IDE refactoring bugs, we don't need to spend extra effort on building another refactoring tool, right? So if you have any connections to Eclipse people or NetBeans people, please let them know that there are still bugs, many bugs, and they are hidden underneath by changing the status to want to fix bugs. And if there's no one who reopen the bugs, they can be permanently alive. And I think they need to know the current status. That is the reason why I wrote this paper.
Yeah, thank you.
Yeah, thank you, Jean-Luc. And yeah, even though we're going again, running it a bit late, but I could not stop this amazing discussion. I'm sorry, so I cannot just do that. So thank you all for this good presentations. And then now we go with our third and last presentation for this session. Before our keynote, we will definitely skip the break. Zarina will be presenting next. She will be presenting the IntelliJ platform, a framework for building plugins and mining software data. So this is already, we have sort of seen how this perhaps manifests, or we have had an idea about it based on the keynote. So Zarina, feel free to share your screen if you want. I already gave you the co-host privilege, and if you want, I can, if you want me to play it on my side, I can also do that. It's just really up to you. Oh, okay, it's here. All right. So make sure not to forget to also, well, how do you call that option in Zoom to assign also this sound, also make the sound also there so we can all hear you.
Okay, hi everyone. Let me check if you hear the sound from the video.
Hello everyone, my name is...
Do you hear it?
Yes.
Great.
Yeah, if you can just make it louder, sure. Cool.
Mm-hmm.
If you can make it a bit louder, that'll be awesome.
I'm researcher at JetBrains Research, and today I will tell you what the IntelliJ platform is and how it could be useful for you. Here's the outline of my today's talk. First, we will shortly discuss refactoring recommendation and the ways to build and distribute research tools, as well as their pros and cons. Then, I will briefly describe what the IntelliJ platform is, list its main features, and show how it would be useful for you in several use cases. After this, we will have a live demonstration where we will implement a basic plugin for IntelliJ IDEA that searches for problems in the code, and in the end, I will be happy to answer your questions. Some of us here will use smart tools to help developers in their work, for example, to maintain code and make it more structured and easy to read for refactoring. This slide presents several example papers in this domain. Refactoring is an important part of the developer's work. Manually checking the code to identify refactoring opportunities might be tiresome, so the tools that could suggest refactorings to resolve the problems in the code are needed. A number of refactoring recommendation systems have been suggested in the literature, so we know quite a bit about the challenges of these tasks and disadvantages of existing tools. First of all, some of the approaches are not open source, and there is an obvious problem with this. The results just can't be replicated and improved. Developers don't have any chance to use them in their work, or at least this is not straightforward. Other tools are implemented as standalone applications and are stored somewhere on the internet, sometimes even without built instructions. Even if developers find a way to learn about your tool, it might be challenging for them to integrate the tool in their work process. Should the developers add an additional step in their work pipeline to use your tool? How should it be integrated? It seems that often there exists a barrier between useful tools and their usage in the developer's daily work. Other tools are implemented as plugins for IDEs. There are huge advantages in building the tools this way. The plugins can be easily integrated into the developer's workflow. A developer only needs to install it into the IDE by clicking a single button. Everything else is usually done automatically. The next advantage is that the plugins could be easily found in the plugin repository by keywords. And finally, the users can provide feedback about the plugin usage, send some feature requests or bug reports straight from the IDE, which is simple for them. This will help the plugin authors to make the tool better. JetBrains develops IDEs that are used by millions of software developers around the world. For example, IntelliJ IDEA is one of the most popular IDEs for Java developers. Like other JetBrains IDEs, PyCharm for Python, C-Line for C++, and others, it is based on the IntelliJ platform. So, what is this platform? The IntelliJ platform allows you to extend the IDE's functionality with some additional features. It provides you with rich capabilities for code analysis, allows you to work with the project, version control systems, and show different kinds of user interface features. The main idea here is that IDEs already do a lot of work on code analysis and manipulation, and there is no need to implement them from scratch. You can already use them directly in the plugins. The IntelliJ platform uses inner representation of source code called Program Structure Interface, abbreviated as PSI. Here's an example of the PSI tree built for the method hello. The PSI nodes represent different code elements, for example, the file list, parameter list, method call expression, white spaces, and so on. It is possible to trigger refactoring from the plugins. There are refactorings that are already implemented in the IntelliJ platform, since you can perform them in the IDE, and they could be triggered directly from the plugins. To trigger refactorings, first you need to decide which elements should be involved. Then you can trigger the refactoring handler from the platform, which is responsible for the refactoring type you're interested in. Each refactoring has its own preconditions that should be passed before performing changes. If a user tries to perform refactoring that can't be done, the IDE shows a dialog with a message with a reason why it can be performed. You can implement your own refactoring as well. To extend the IDE's functionality, you need to use extension points. For example, you need to use them when you want to add a new action to an IDE's menu. There are more than 1,000 extension points available in the platform, so you'll have a lot of ways to extend IDE's behavior. In order not to get lost in these many opportunities, you can use the IntelliJ Platform Explorer. It can help you find usages of extension points in the existing plugins that are hosted on Git. You can specify the name of the extension point you're interested in, the language the plugins are written in, and the build system. In the Explorer, will show you a list of plugins that use the extension point. Then you can go to the plugin from the list and inspect its source code. In the example on the slide, we can see the results of the search for the usage of the line refactoring handler. You can wrap your tool in a plugin from IntelliJ-based IDE and spread it around by publishing in the IntelliJ plugin repository called Marketplace. Millions of IntelliJ-based IDE's users will be able to find your tool within the IDE and download it. You will also be able to make some updates to your plugin, and the users will be notified about them in the IDE. Additionally, it allows you to get some feedback and feature requests from users in the plugins page in the plugin repository. And it's up to you to share your tools for free or set a price for the plugins usage. There is a Slack workspace you can join to get help with developing plugins using the IntelliJ platform. Other plugins developers and JetBrains employees could help you and provide some advice. Let's now see how the IntelliJ platform might be useful in the example of several use cases that software engineering researchers face. The first use case is mining data. This can be used, for example, for large-scale code analysis or for gathering data to train machine learning models. The IntelliJ platform allows to analyze not only source code of the projects, but also its changes history. You can get commits, changes from them, and some details you're interested in. It is important to mention that you can run your plugin as a command line application, which might be useful if you want to run calculations on the remote server. As an example, let's take a look at the IntelliJ IDEA plugin called Psi Miner. It was presented this year on the MSI conference. Psi Miner allows you to mine PSI trees from Java and Kotlin projects and create data sets for machine learning models from them. The plugin runs as a command line application, processes the given projects, and save the remaining data into one of the several supported formats. To show the benefits of the usage of PSI trees, the authors compared the results of the popular machine learning model with using simple ASTs. For the experiment, the authors choose a code-to-set model that suggests names for methods. It uses paths in the ASTs as an input. The results shows that the model trained on PSI shows better results than the one trained on simple ASTs. Here's an example of the PSI tree built for the getChar method. As you can see, the tree contains some additional information, as well as types, names, and rotation. The second use case is running machine learning models. It can be beneficial to embed a machine learning model into the plugin to make it available to users. This can be done, for example, by using the K-inference library, which makes it possible to execute machine learning models in Kotlin and Java applications. Here's an example. There is an IntelliJ plugin called IWoR, which suggests better names for variables in Java and Kotlin projects. It uses an n-gram model to generate candidates for variables names and shows a list of candidates with probability for each of them. When a user selects one of the suggestions, the plugin performs rename variable refactoring automatically. The next use case is visualizing information. It might be useful to show some information to the developers that might help them in their tasks. You can add tool windows, notifications, embed some information in the editor, or even encode diffs. The example here is Refactor Insight, a plugin for IntelliJ ideas that could help developers during inspecting code changes. It detects 40 refactoring types in Java and 90 refactoring types in Kotlin. To detect refactorings in Java and Kotlin code, the plugin relies on Refactoring Miner and Kotlin Miner respectively. Refactor Insight allows users to inspect code diffs with auto-folded refactorings and hints with short descriptions of them. Now let's see Refactor Insight in action. User needs to open the Git log tab. Here, select any commit in the list and select any file that was changed in that commit. The Diff Window opens with code changes. You can see that there are hints with short descriptions of the performed refactorings. The folding and the hints decrease the number of lines the developers need to read and analyze. If a user wants to see the code, they can expand it. The final use case that we will consider is refactoring recommendation. Developing a new refactoring recommendation approach is a challenging task in itself, and the need to implement the refactoring support makes it even harder. As we have discussed before, the IntelliJ platform supports automatic refactorings that are already implemented and could be triggered from the plugins. There is a tool called JDeodorant that detects several code smells in Java code and recommends appropriate refactorings to resolve them. This tool was originally developed as an Eclipse plugin. In our research group, we migrated this tool to the IntelliJ platform and released a plugin called IntelliJ Deodorant. Originally, JDeodorant uses Eclipse.dt to analyze the code and visualize results. So we cut Eclipse dependencies and used PSI instead to analyze the code. The most important part here is that we use the automatic refactoring that's already implemented in the IntelliJ platform. Here you can see what IntelliJ Deodorant looks like. And the last part of today's talk is a live demo. During the live demo, we will learn how to create a basic IntelliJ IDEA plugin, how to analyze code, and how to attract the user's attention to the problems in the code. I have created an empty project for plugin. IDE has configured Gradle for us. We will write our plugin in Kotlin, and we will use IntelliJ platform. Here you can see some dependencies, Kotlin, some IntelliJ settings. Here defining in the Gradle properties file. Our plugin will work in IntelliJ IDEA Community Edition version of 2021.2. Here's pretty important file, plugin XML. Here we should put information about our plugin, its name, information about the vendor, description of our plugin, some dependencies on the IntelliJ platform models we use, extension points, and actions we have in our plugin. We have to register them here in these two blocks. So let's start. We will implement two basic inspections, and then we'll run them to check how they work. First inspection. Let's call it nylon method inspection. This inspection will walk through methods in Java class, check the number of lines it consists of, and if the number is larger than 40, it will highlight this method. So we will learn how to add a basic inspection, how to analyze the code, and attract users' attention to some problems in the code. First of all, we should extend our inspection from the base inspection class that's called abstract base Java local inspection tool. Okay, we should write method called build visitor, and we should implement a visitor for the code. Let's call it my method visitor. Oops. It will have one field called folder, and we will pass it here. So visitor and pass folder here. So we should extend our method visitor from the base Psi element visitor class. And we should override one of its methods. As you can see, we have several options depending on the elements we want to visit and process. In our case, we want to visit methods, but we can visit comments, files, and so on. Let's choose first one, visit element. First of all, we should check if the element is method. We can check the type of the. We can check the type of the element. If the type is Psi method, it means that it's a method. Psi represents methods in Psi tree. Okay, let's create a variable for our method. Then we should check, we should calculate the number of lines that the method consists of. We can get methods, a text representation of method. And let's check if it is larger than 40. And if it is true, we should register a problem. We can do it using folder. Here, method register problem. We should pass the element we want to highlight, and the message we want to show. For example, the method is too long. Okay. Next thing we should do is to implement outline method. IDE suggests us to create function. Let's do it. Okay. It should return number of lines. The method can consist. Okay. Let's get text representation of method. Get all characters it consists of by running by using this method char array. Then let's count new lines character. Let's check if character is equal to /n, or character is equal to /r. Okay, it seems our inspection is ready. The next thing we should do is to register this inspection in the plugin XML file. Let's do it. We should edit in the extensions block, local inspection, and we can set some properties. One of them is language. We will analyze Java code, so let's choose Java here. Then display name, long method. Okay. Next thing, group name, long method. Level, warning, will be a warning. We can also choose error or some other level, but let's make it just a warning. Let's enable it by default. And also we should specify the implementation class. I love method inspection. Second example I would like to implement together is an inspection that searches for long conditions in if statements that might be hard to read and analyze. It could be extracted into separate methods. So let's call it my if statement inspection. We also should extend it from the abstract base Java local inspection tool. Let's override the visitor method as well. Also, we should implement our visitor. Let's set a field folder. Let's extend it from Java element visitor, and let's override visit if statement and if visit if statement. As you can see, there is a lot of code elements we can visit, but in our case we should select visit if statement. First of all, let's check if statement is not null. Statement is null. Just return. Okay. Then let's get the condition. We want to analyze the conditions. Condition. And if the condition is null, we will return. Okay. Next thing we should do is calculate length of the condition, and then if it's longer than, for example, 40, we will show a message. We will highlight this condition and show a message that the condition is too long. So let's get a check. If condition text length larger than 40, let's register a problem, and we'll pass condition to highlight and the message condition is too long, be extracted. Separate method. And here we should return our new visitor. And the last thing we need to do is to register our inspection in the plugins XML file. Language Java, display name long condition, word name is also called long condition, long if condition. Let's enable it by default. Let's make it, and let's define validation class. Right, statement inspection. Okay, it looks like we're ready to test it. Let's do it. First of all, we need to build our plugin. There's a plugin we need to execute run ID task. It will open new instance with the idea with our plugin installed. And let's see if our inspection worked as we expected. Yeah. Here we can see a pretty long method that consists of 48 lines, and our plugin highlighted this method and shows a message that method is too long. So the inspection works as we expected. And the second example, the inspection that searches for long if conditions. And here we can notice one. Yeah, plugin highlighted the long condition, and it shows a message that the condition is too long. It consists of 129 characters. Okay, nice. Okay, we have implemented a basic plugin from the idea. Implemented 2 simple inspections, learn how to analyze the code, the different kinds of PSI nodes, and we checked how it works. So I hope you found this demo useful. Thank you for your attention. Here are the QR codes to the repository with the plugin examples for each use case we have discussed today. They could serve as templates for your plugins. And the QR code to the ML4C laboratory. I would be happy to answer your questions.
All right, thank you, Zarina, for this presentation. So yeah, it's good to see how we can use this powerful IDE to build plugins. So questions from the community, Anthony?
Yeah, I have a question. I have a couple of questions, but first, thank you for the demo. It was really useful because I'm actually looking into IntelliJ plugins, and so this was really insightful. So my first question is regarding the demo that you showed, right? So I noticed that in your demo, you utilized classes that are specific to Java, like you inherited from abstract-based Java local inspection tool. So does this mean that this plugin will work only on IntelliJ IDEA, or can it work on like the other IDEs like PyCharm and WebStorm?
Anthony, thank you for your question. Our plugin will work only in IntelliJ IDEA because we have only we have dependencies on the IntelliJ IDEA only. And as you mentioned, our plugin will work only with Java code. But if we want to make it work with Kotlin, we should do several changes, but it's possible. We can make our plugin work with several languages. And in case of IntelliJ IDEA, could be Java, Kotlin, and if I'm not mistaken, Scala is also possible.
Okay, because I mean, so like for example, the long method, right? So long method is common in say Java and say, you know, Python and PHP, right? So if I would, that means, do I need to write that? Do I need to write 3 different plugins, or can I just write one plugin that just works on all 3 IDEs?
I would say you can make some language independent functionality and reuse it in different plugins. But yes, if you want to write a plugin for Python, it should be a different plugin. So you need a plugin for Java and a plugin for Python, but they can reuse some base functionality that is no language specific. You can implement it as a separate library, for example, and then use it in both your plugins as a dependency.
Okay. So if I correctly understood, is it because we have differences in the PSIs, or because we have specific IDEs for each language? What's the reason behind that?
Yeah, there is a difference in PSI too. But you know, there is some representation of PSI that works for both languages, for Java and Kotlin. You could Google it. It's called UAST, Unified Abstract Syntax Tree, that could work with both languages. But yes, to process code in different languages, you should do it in several plugins.
Anthony,
Okay.
does that answer your question?
Yeah, it does. So
Awesome.
if I can ask you just one more question.
Sure.
So again, in your slides, Zarina, you mentioned that it's possible to run the plugin as a command line tool, correct? So like how would so do I need to have the JetBrains IDE installed on my machine to run it as a command line tool? How does that work? Like take, for example, your long method inspection tool. If you want to run that as a command line tool to scan, say, multiple files in multiple projects, like how would that work? Do you need to build a separate, command line jar tool, or do you just call the IDE?
What you should do, you should, yes, first of all, you can run your plugin in the headless mode. It's called headless mode. It means that it will not open user interface of IntelliJ IDEA. To make it work, you need to build your plugin and then just run it in the terminal as other Java application, and it will do all analysis. It will do all analysis you need, and will not open IntelliJ IDEA instance. You don't need to install IntelliJ IDEA. It will do all analysis in its own. I mean, it will it will not open IntelliJ IDEA. So it's just like a command line Java command line application.
Okay, so basically what I still need to install the IDE, but instead of double clicking the IDE, I just call it in command line mode with some arguments, correct?
To develop a headless plugin, you need IntelliJ IDEA to write.
No, not to develop, to actually run it, to run the plugin.
No,
say like your code inspection tool, like the long method. If I want to run the long method plugin as a command line tool.
Yes, you can run it as a command line tool. We can run inspections in if you want to run the inspections in command line, you can do it. So you don't need to open IntelliJ IDEA. It will do all analysis without user interface.
Okay. All right. Yeah, that makes sense. Okay. Thanks so much for answering.
Nicholas, correct. Yes, it will be downloaded as a dependency, and we'll use IntelliJ platform capabilities and use it test. Thank you for questions.
Thank you, I guess, Zarina, for this presentation. Thank you, Anthony. Thank you, everyone. So I guess we can now move to our next keynote. So Professor Santanis is being here, and thank you again for accepting to do this. So our next keynote, Professor Santanis, his keynote will be about refactoring mining. So we've been all familiar with this, his research, and this research has been very useful to our community. So I'm very excited myself to hear his keynote, and yeah, we can start now. So Professor Santanis, do you want me to play the video, or you want to play it on your side?
Yes, please, if you can play it on your side, it will be...
Sure, yeah, I can do that. So let me open it, and then I'll share my screen. Okay, it's here. Let me do this, and then I'm going to make sure I have that option available. I'm going to share my screen. Just 1 second. Screen 1. Okay, and then I have to make sure I also allow the sound. Share sound. Okay. So let me know if you guys can hear this. I mean, I'm gonna just first of all also increase the volume.
It is a great pleasure to give the keynote for...
It works. Okay, awesome. Okay, then let's start.
It is a great pleasure to give the keynote for the refactoring workshop, as it is very close to my heart. In 2019, I had the privilege to organize the last in-person refactoring workshop in Montreal. And as you can see from the picture, it was a great success. Not just because everyone is smiling, but mainly because many great ideas and collaborations were born in this edition of the workshop. If somebody asks me, what have I done for refactoring, I would answer simply with 2 words. JDeodorant and Refactoring Miner. So JDeodorant is a refactoring recommendation tool that I started developing as a PhD student. Obviously, throughout the years, there were many newer techniques that had better precision and recall. However, I'm very proud of this work because it kept its promise, which was to support all activities of the refactoring process. The second tool is Refactoring Miner, and as you can understand from the name, it's a tool that can detect refactorings in the commit history of projects. Now, in the first part of my talk, I will focus on the story behind Refactoring Miner. The story started right after I graduated from my PhD under the supervision of Alexander Hadjigeorgiou, who was a great mentor and shaped me as a researcher and as a personality. So then I moved to Edmonton and the University of Alberta, where I did a postdoc under the supervision of Eleni Stroulia. As you might know, Eleni Stroulia, together with Zhengchang, they developed UML Diff and JDevan, which was the state-of-the-art refactoring detection tool back in the mid-2000s. This tool was great, but it was a little bit difficult to use, as it required to import 2 versions of a project inside Eclipse, build them without any compilation errors, and also it had a database as the backend, which was quite challenging to set up. So when I joined Eleni's lab, Eleni had a master student, Fabio Rocha, who was working on developing JDevan as a web service so that it's easier to use. Fabio had developed a lot of tooling and infrastructure in order to process SVN commits and also being able to create from commits Eclipse projects. So this gave me a lot of inspiration to start working on a refactoring detection tool that is able to process commits. And with this version of the tool, we published our first related work on CASCON 2013, which I call version 0.0. So in this work, most ideas for the detection of refactoring were inspired from UML Diff. The structure of the method bodies was completely ignored. The only information we're storing about method bodies was method calls and field accesses. And as you can see from the table on the right, most refactorings were detected based on signature matching. In the paper, we provided only precision, which was very high, but this was easily explained because the rules were very strict, and as a result, there were very few false positives. And our evaluation included only 3 systems. Despite all these limitations, this work had a very interesting research question, which was, what is the purpose of the applied refactorings? To investigate this question, we manually examined all detected refactorings in these 3 systems and came up with a catalog of motivations explaining the reasons that the developers applied these refactorings. Here you can see an overview of the catalogs for extract method and inheritance-related refactorings. As you can see, the motivations are related to code smells, extending the code, backward compatibility, and refining the abstraction level. So after I finished my postdoc at the University of Alberta, I moved to Montreal and Concordia University to start as an assistant professor. However, I didn't work again on this research problem of refactoring detection. And what was the reason for that? The reason was that RefFinder, which was back then the state-of-the-art refactoring detection tool, had a very high precision and recall reported in the paper, which was 74% precision and 96% recall. So this very high recall number made me very hesitant to work on this topic because I thought it was impossible to further improve. However, if you read more carefully the paper, you will see that the authors constructed their oracle using their own tool with 2 different similarity thresholds. And this is a big bias for the oracle because it doesn't mean that even using different thresholds, the tool is able to detect all possible refactorings done in the history of projects. So the first lesson that we can learn is that we should not be intimidated by super results that we read in the papers, and we should always question these results. There is always space to further improve. So as I said, I stopped working completely on this refactoring mining topic until one day I received this email from Danilo Silva and his supervisor, Marco Tullio Valente. I already knew Danilo because I was the examiner for his master thesis. And basically in his email, he's asking if it is possible to share the source code of the tool that we used in the CASCON paper I talked to you about before. Obviously, I was very happy to share the code. However, this code luckily was stored in an external hard drive. I didn't make any repository for it. And it was in this compressed file named XMI diff. If you wonder why the name XMI appears there, is because the tool back then was also possible to compare UML class diagrams with source code in order to check if there is a drift between the original design and the actual implementation of the code. And the UML class diagrams are exported in a file format called XMI. So the second lesson we can learn is that we should always make our code and data available in a repository. And the reason is that it is not possible to know what this code and this tool can enable in the future. And at this point, I would like to talk to you about some open science initiatives. So here, as you can see in this chart, we see that the majority of the software engineering and programming language conferences have introduced an artifact evaluation track. So all accepted papers can submit a separate artifact submission that is evaluated by an independent committee. And according to some criteria, the paper gets some badges. And also I would like to mention that this year, ICSI 2022 had a mandatory field where the authors had to explain and provide the data availability. They have to give a link to their dataset or tools, or explain why this was not available, and this was a mandatory field. So this shows that our science is going to the right direction, because it's not acceptable to have papers published that cannot be replicated. So after a while, Danilo and Marco came back to me and said, okay, let's do an empirical study about refactoring. We discussed about it and I said, of course, but I think we should start the question about why we refactor, because I was not satisfied with the way I did it back in the Cascon work. At this point, I would like to thank and acknowledge Danilo and Marco, because without their bugging me, the whole refactoring mining research would never have started. So I'm deeply thankful to them about all this collaboration and the work that came after it. So we started working for an ICSI paper that we submitted in 2016, and this can be considered as the version 0.1 of Refactoring Miner. So in this work, Danilo developed the API of Refactoring Miner. He developed a lot of tooling for checking out and parsing Git commits. He developed an infrastructure for monitoring GitHub projects for refactoring activity, and also for automatically generating emails to contact developers in the case where we were finding some refactorings in the commits. And finally, he also created a web application that could support performing a thematic analysis on the collected responses from the developers in order to come up with the motivation themes. So we followed the Firehouse interview method, where we monitor 124 GitHub projects between June and August 2015. We sent in total 465 emails and we received 195 responses, which is a 42% response rate. In addition, we had 27 commits for which we already had the reason behind the refactoring in the commit message. And after doing the thematic analysis, we compiled a catalog of 44 distinct motivations for 12 different refactoring types. So the output of this work was a catalog of motivations. So here you can see the motivations behind the extract method. This refactoring type has the most diverse motivations. We found 11 different motivations for applying this refactoring. And also we made available the artifact, which included all instances of refactorings that we found, along with the responses of the developers, the motivation tags that resulted after our labeling, and also some answers related to the usage of refactoring tools, whether refactoring was applied manually or with the use of a tool, and if it was applied manually, what was the reason for that. So we're very excited about this work. However, when we received the reviewer comments, we found out that the paper was rejected. And actually, one of the reviewers had the wrong claim, was saying that we used RefFinder as a tool, which is known to have very poor precision and recall. And that although we tried to eliminate false positives by manual inspection, we didn't do anything related to the low recall of the tool. So this was obviously a false claim because we were not using RefFinder, we had developed our own tool. So we contacted the program chairs to let them know about this mistake. In turn, they contacted the reviewer who admitted the mistake. However, still the paper was rejected because there were some other issues about that. Okay, after this disappointment, we learned this lesson that even ICSI reviewers can make mistakes. However, we shouldn't get disappointed. We should always try to improve, advance the current state of the art in the evaluation and resubmit. So we attempted to resubmit this work again to FSC in 2016. One of the changes that we made is that we renamed the tool in the paper from Ref Detector to Refactoring Miner in order to avoid any other misunderstandings. So this was the time that Refactoring Miner got its official name. And we also, of course, addressed most of the reviewers' comments. So after a while, we got the results, the paper was accepted, and a few months later, we also learned that the paper received not just one, but 2 awards, a Distinguished Paper Award and a Distinguished Artifact Award. Obviously, we were very excited about this recognition of our hard work, and we started thinking about what would be the next steps. Danilo and Marco were already started working on their own tool, which eventually became RefDiff and was published in MSR 17. So there was some discussion in order to make a common paper that we would compare RefDiff with Refactoring Miner. However, this Refactoring Miner didn't have any of my ideas, and I was not 100% satisfied with the way it was working. So there was a lot of space of improvement, and I needed time in order to implement these ideas and test these ideas. So at this point, our paths separated, and Danilo and Marco continued working on RefDiff, while I started with my team working on a rebirth of Refactoring Miner. So this brings us to the myth of Hercules related to the crossroads that he faced. So here you can see Hercules that is in front of 2 paths. On the right, there is Vice. This is a young and attractive woman that is pointing Hercules on a path that is downslope, well paved, very easy to go through, and it leads to immediate success and happiness. However, as we can see in the background, in the long term there is some disaster coming. Now on the right side we see Virtue. Virtue is like an old, exhausted lady that is pointing Hercules to a mountain that is very hard to climb, very steep mountain. However, if you work hard, we can see that justice can be made that can help you climb this mountain. And after achieving climbing this mountain, you can reach eternal honor. So the Hercules crossroads actually resemble what can also happen in science. We can always take the easy path and publish first and receive the immediate benefits of having the first publication in a field. However, giving the best solution requires way more hard work, but eventually it can lead to a long-term impact. So now this leads to the first version of Refactoring Miner 1.0 that was submitted to ICSI in 2018. So what were the limitations of previous approaches? The first limitation was that they were depending on similarity thresholds. However, a lot of research has shown that these thresholds cannot be universal and cannot work well for every project, as projects have very different characteristics and need different calibrations. The second limitation is that before, especially before RefDiff, all tools were depending on built versions of projects in order to detect refactorings. However, as we have seen in other studies, only a small percentage of the change history can be successfully compiled. And this is a big blocker for doing mining studies over the commit history. And the final limitation is that all previous tools, they used unreliable oracles for evaluating precision and recall. So these oracles were either incomplete because refactorings were found in release notes or commit messages, which we know developers do not document every refactoring that they do there. either the oracles were biased because a single tool was applied with two different similarity thresholds in order to make the oracle. And we have cases of artificial oracles where, for example, some students had applied some random refactorings on projects. However, although in this way you can accurately compute the recall of your tool, these refactorings are not representative of real refactorings because, first of all, they do not meet any real requirements, and second, they don't come with the noise of overlapping changes that usually happens in commits. So we decided we will develop an approach that the thresholds will be banned, so no thresholds will be used there. So how we achieve this, I will show you through an example. So think now that we have this method, and in the next commit, you see that there are some changes happening in the methods. First of all, the return type of the method is changing from an array of address to a list of address. In addition, we see that a new parameter is added to parameterize the ports value. And then we see that this try-catch block is extracted into another method in order to be reused. And also all the values, the arguments that are passed in order to create the address object are parameterized through the parameters host and port. Now, if we had an approach to compare the similarity of statements, we would see that these two statements that I highlight here that create the address object, that were originally the same statement, have become textually different. So if you compute the textual similarity of these two statements with, let's say, Levenstein distance or bigram similarity, you will get a similarity of 30%, which is very low. This means you would need a very low threshold to match these statements that would introduce other problems in having wrong statement matches. So we address this problem by applying three techniques. The first technique is called abstraction, which means basically when you have assignment statements or return statements, we compare only the expression that follows the assignment or that follows the return statement. In that case, it would be the creation of the address object. The second technique we applied is called argumentization, which basically means when we have extract method or inline method refactorings, we replace the parameters with the actual arguments passed when calling the extracted method. As you can see, the two statements are becoming more and more similar. However, they still have one difference, which is this ports variable. So the third technique that we apply is that we perform all possible AST node replacements for the nodes that are different between the two statements until we succeed to make the two statements identical. So here, by replacing ports field with the port's local variable, we can make them having a 100% textual similarity, and thus we can match these two statements without using any kind of similarity threshold, just by taking advantage of the refactoring mechanics. So to tackle the third challenge of building a reliable oracle, I had the great help of my students. Matin, who was a master's student back then, Lale was a postdoc in the group, and Davud was a PhD student. So what we did is that we used the dataset from the Why We Refactor paper that I talked to you before, which included 538 commits from 185 open source projects. We executed both available tools at the time that could work on commits, and this was our tool and refdiff. We converted the output of the tools to the same format, and we manually validated all refactoring instances, which were around 4,000, out of which 3,200 were true positives and 900 were false positives. The validation process was labor intensive and involved 3 validators for a period of 3 months. And to compute recall, we consider the union of the true positives reported by both tools as the ground truth. The idea behind this is that as the number of the tools increases, and especially if the refactoring detection tools use different methods for detecting the refactorings, the ground truth will become more complete. We also created a web app to help us in the validation process. So here you can see a refactoring instance, extract method refactoring instance. You can see all the tools that detect it. We had links that lead directly to the line the exact line where the refactorings happened. And there we can see different validation options, as well check who participated in the validation. And also we were able to enter some free text comments for our communication. So in comparison with RefDiff, we can see that Refactoring Miner achieved almost 20% improvement in precision. However, still the recall of the tools were very similar. So if I want to do a retrospective about this work, I can say that our solution was still far from perfect. And this was because there was a lot of time pressure. It was very urgent to establish Refactoring Miner with a publication after RefDiff was already established. We had the ICSI deadline that was on August 25th, but we even had an even more strict deadline, which was the birth of our daughter Sophia, which was expected on August 15th. So we really had the pressure to finish all this work at least 1 week before Sophia's birth. So despite working over 1 year on this paper, there was still a lot of space for improvement. And one more problem that I faced is that the entire team graduated after this work. So at some point I was left alone working on this project. So this leads to the next version of Refactoring Miner, which is the most mature version of the tool. In this work, we added support for more replacements types, as you can see in table 5. And this actually increased the number of statements that we could match. We also added support for 20 new sub-method level refactoring types. That means refactorings taking place inside the body of a method, such as variable renames and so on. We also supported nested refactoring detection. Imagine having a method extracted from another extracted method. We also used refactoring inference. The Refactoring Miner had an inherent limitation that it couldn't find refactorings for methods that didn't have a body, such as abstract method or interface methods. So in that case, we used the information collected from methods overriding these abstract methods in order to infer refactorings in the signature of the abstract methods. And finally, we also improved the matching of method calls to method declarations with argument type inference. That means understanding the type of a parameter based on the actual argument passed when calling an extraction method or an inline method. Then, with the help of Ameya Ketkar, who joined our group between September 2019 and December 2019, we tried to build an even more reliable oracle. So we executed all available tools at the time. That was 2 versions of Refactoring Miner, 3 versions of RefDiff, and 1 version of Gumtree Diff, which is an abstract syntax tree diff tool. We converted the output of the tools to the same format, and we validated over 5,800 new unique refactoring instances, out of which 4,000 were true positives and around 1,800 were false positives. And we finally built an oracle that had over 7,000 true positives for 40 different refactoring types, and 72% of these instances were detected by 2 or more tools, which gives more reliability to this oracle. Now if we go to the precision and recall results, we can see that compared to the previous version of Refactoring Miner, we have a 3% improvement in precision. However, the big improvement is in recall, which is over 13%. And then compared to the latest version of RefDiff, we can see that we have like a 6% higher precision, but the big difference again is in the recall, which is almost 20% better. In addition, we developed some refactoring detection rules based on the output of Gumtree Diff in order to find refactorings within the body of methods, such as renaming variables, parameters, fields, changes in return types, changes in variable types, and so on. And as you can see in the final results, we had an impressive improvement over Gumtree. So the improvement in precision is 39%, while the improvement in recall is 30%. Currently, we're working towards version 2.2, which is the most advanced version at this point. Just to give you one feature that it supports the detection of loops and if statements converted to the Stream API for reads and filter, as you can see in this example. So right now it supports 85 different refactoring types. There are 10,900 validated true posits in the Oracle. The precision is reaching almost perfection, 99.7%. The recall is 97%. And it is the most tested and reliable version we have. It has been tested on over 200,000 commits without having a single exception. And there are also now many independent studies that confirm that this tool has the best precision. So based on our experience, what it takes to make a reliable and usable tool? So at minimum, it takes 5 years of research and development. It needs extensive testing. Right now, we have a test suite that runs all commits in our Oracle, and there is no code committed if it doesn't improve precision or recall, or at least keeps it at the same level. We have very detailed documentation. We have a README file in our GitHub project with API code snippets and also help guidelines in order to run the tool in command line mode. We are supporting our users. We have over 200 issues that were resolved in our issue tracker. We have a stable project leader. I noticed throughout the years that many projects die because they were just run from a student who graduated and there is no one to continue supporting them. So it's very important to have a stable leader in the project. And also I had a great team of people that I collaborated with and really made the difference in improving this tool. In the second part of my talk, I will discuss about the promises of refactoring mining. And I will use some quotes from the original Refactoring Miner paper about the potential applications of refactoring mining, along with some papers as examples that fulfill these promises. The first promise was that refactoring mining can help researchers to replicate existing empirical studies and refute or confirm previously held beliefs. Obviously, there are many empirical studies that were done about refactoring. However, I would like to focus on two of them because they were giving a bad name to refactoring, and I always thought that this was a bit unfair. So the first study on the left investigated the relationship of refactorings with bugs, and it found that 15% of the bugs are actually induced by refactoring. Moreover, if we're talking about inheritance-related refactoring, this percentage increases to 40%. So this means inheritance-related refactorings introduce more bugs than other refactorings. On the right, we see a study that investigated the relationship of refactoring with regression testing. And in particular, this work found that 38% of the failed tests involve some refactoring. Obviously, both papers give the message that refactoring has very negative impacts on maintainability, as it introduces bugs and also it leads to test failures. However, both studies had some serious threats to their validity. Both of these studies relied on Reffinder, which at the time was the state-of-the-art refactoring mining tool. Later on, independent studies have shown that Reffinder had quite low precision and recall. Soares and his colleagues in 2013 computed a precision of 35% for Reffinder and an recall of 24%. Later on, Kadar and his colleagues in 2016 computed a precision of 27% for Reffinder. Here I just want to remind you that the original Reffinder paper was claiming a precision of 74% and 96% recall. So we can see there is a huge gap between the results reported by the authors of Reffinder and the independent studies. Now, both of the studies, because they were using Reffinder, they collected refactoring information at release level. This means between two versions of a software system. And this led to perform a very coarse-grained analysis that in turn led to some strong and unsafe assumptions. Both of these studies were later on replicated by these two new studies that used Refactoring Miner as the mining tool. As a result, they were able to collect refactoring information at a very fine-grained level because Refactoring Miner not only gives you the exact commit where the refactoring took place, but also the exact line numbers involving the refactorings. And in addition, both studies did a very extensive qualitative evaluation in order to validate their findings. Now, in the study on the left, the authors found that in a sample of 384 commits where the SSZ algorithm was blaming refactoring for the introduction of the bugs, they found that 62% of these bugs were actually unrelated to refactoring. Now, the study on the right found that only 2.5% of refactorings actually break tests, and these are some specific refactoring types related to the signature of the methods, such as adding parameters or changing the return type. So here we can see that using a more accurate tool and having a better experiment design can actually lead to completely different results. An important lesson that we can learn here is that when we are developing a tool, this comes with a very huge responsibility for the authors of the tools. This is because this tool can be later on used to conduct empirical studies or build other tools upon it. So this means we should go above and beyond when evaluating its accuracy. We should make sure that we are extended all our capacity when evaluating the accuracy of such tools. The second promise is that Refactoring Miner can actually be used to reduce the noise created by refactorings and significantly improve the accuracy of other tools. So here I would like to talk about two works that took some existing techniques and made them refactoring aware. The first one is a refactoring aware version of the SSZ algorithm. So this is an algorithm that actually finds the commits that introduce the bug. And they found that the refactoring aware version improved the percentage of valid bug introducing lines by 8% over their previous approach, while it also improved the median percentage of valid bug introducing lines per bug fix by 15% over the previous approach. On the right, we see IntelliMerge. IntelliMerge is a refactoring-aware merging tool, and according to the experiments of the authors, they found that it reduced the number of merge conflicts by 59% over Git merge, which is the standard merging tool used by developers, and by 12% over JFST merge, which is the state-of-the-art structural merging tool. So here a lesson that we can learn is that if we make existing code evolution analysis techniques refactoring aware, we can significantly improve their accuracy. The third promise is that the oracle that we created of the true refactorings from 538 commits across 185 projects provides an invaluable resource for validating novel refactoring tools and for comparing existing approaches. So here I would like to discuss two tools, namely RefDiff 2.0 and RefDetect, that followed the first version of Refactoring Miner. Both of these tools are multi-language tools. That means they're language agnostic and they have a technique that can be applied in many different languages. Both of these papers, they used our own oracle in order to compute the precision and recall in Java projects, and also of course compare it with the Refactoring Miner tool and other tools. The fourth promise is that refactoring mining can enable online refactoring detection on partial input when a developer inspects a code diff to review a change or tries to understand code evolution selectively. So here I would like to focus your attention on having partial input. That means having only part of the files to perform the refactoring detection, and also having a selective evolution. That means detect refactorings and changes specifically on a program element of our interest. The current state-of-the-art work on method tracking is called Sovel. This is a tool that can quickly produce the complete and accurate change history for 90% of the methods, and this history includes 97% of all method changes. This tool is partially refactoring aware. This means it supports method signature changes, it supports method moves, and it supports also file renames and moves. In order to track a program element, it uses thresholds when comparing, let's say, two methods, and these thresholds were calibrated on a training set of 100 methods. It has, however, one limitation. It mismatches methods from which a significant part of their body has been extracted. So this means that it will match an extracted method with the original one if over 70% of its body has been extracted to this new method. On the other hand, it is ultra fast. It takes less than 2 seconds to fetch the entire change history of a method. So together with my master student Mehran Jodavi, we tried to tackle the following challenge. How can we take advantage of Refactoring Miner's high accuracy in a way that is not so computationally expensive? And the solution that we came up with is to do partial and incremental commit analysis based on the location of the track program elements. So this means we execute Refactoring Miner in some rounds, and in the first round we give the minimum possible input to our tool. This is the file containing the track program element in the child and the parent commit. So at minimum we can give 2 files. If we're not able to track the program element with this minimum input, we keep increasing the number of files given as input to Refactoring Miner until we track the file or until we find that this program element was introduced in this commit. Here are the results of the experiments we did. Now, for method tracking at commit level, that means finding all the commits where a change happened, we improved the precision over code shovel by 7.5% and the recall by 3.7%. While at change level, that means reporting the exact changes that happened in each commit, we improved the precision by 9% over code shovel and the recall by 6%. Also, we are the first tool of its kind to support variable tracking with a very high accuracy. So at commit level, we achieve a precision and recall over 98%, while at change level, we achieve a precision and recall over 97%. On the right, you can see 2 volume plots with the execution time distribution of the 2 tools. So on the far right, you can see the code shovel execution time. On median, it takes 2 seconds to extract the entire change history for a method, while Code Tracker, our tool, takes 3.5 seconds on median to extract the entire commit history of a method. So although our tool is slower than Code Shovel, as you can see, it is more accurate, and still the execution time is in the same order of magnitude. The 5th promise is that we can integrate refactoring mining with diff and code review tools in order to raise the level of abstraction for code changes originating from refactorings, and thus help developers to better understand the code evolution. The work that I would like to discuss related to this promise is smart commit. So smart commit is a technique that can decompose a composite commit into distinct activities, and it achieves a median accuracy between 71 to 84% when decomposing composite commits without the involvement of developers. The way the authors achieve this result is by introducing the diff hang graph. In this graph, the nodes represent diff hangs, while there are 4 different kinds of links connecting these nodes. We have hard links that represent syntactic constraints between the AST nodes. We have soft links that represent repetitive change patterns. We have refactoring links that represent edits in different locations which, however, originate from the same refactoring. And finally, we have cosmetic links that represent changes in comments and reformatting. Now, by computing the weights over these links and by partitioning the graph, the developers can find distinct activities in the commits and thus decompose the commit.